sponsors that are listed down here that make this event even possible. We have 4 sessions today. The first one will end at 10:45. Then we have a 30-minute break, and then another session, and then we break for lunch between 1 and 2. Unfortunately, we can't provide food, so you'll have to find food. There are several restaurants scattered around the campus. And without further ado, I think we can start the session. Each talk will be 15 minutes, 12 minutes for the talk and 3 minutes for Q&A. And to kick things off is Eliyahu Horowitz from the Hebrew University. He's going to tell us all about maps and atlases.
All right, so good morning, everyone. And thanks, Shai, Raja, and everyone who helped organize this. And thank you all for coming at 9 o'clock in the morning. I know it's way too early. So let's kick things off. So today I'm going to speak about what can we learn from million models. My name is Eliyahu Horowitz. I'm just finalizing my PhD with Yedid Hoshen at the Hebrew University. And yeah, today we're going to speak about what can we learn from a million models. And specifically, I'm going to describe what can we do with them. This is a model atlas, we call this. It's not actually a galaxy. It's not deep space. It's about 200,000 models from Hugging Face. And throughout the talk, we'll see how can we use them and what can we do with this model atlas. So the thing that enables all of this is what we call the model atlas. And we have basically millions of publicly available models. And in order to navigate them, in order to make sense of them, we need to chart the model atlas. So let's define this model atlas. Basically, it's a directed acyclic graph where each node is a model. Each edge is a weight transformation between one model to the next. So think of things like fine-tuning, training, etc. And then we also have edge features. These basically describe the weight transformations, so we can attach to them things like the optimization hyperparameter, the training data, the transformation type, etc. And we have node features. These are the traits and metadata. So traits are functional attributes, things that the model actually learned, things like accuracy, robustness, etc. And we have the descriptive properties, things like the creation time or license. In order to visualize all of this, we color each node and we change the size of the node. And finally, an important note is that the spatial location has no meaning. So because these graphs are highly non-planar, we need to visualize them somehow in 2D, so we lay them out, but the spatial location of the nodes mean nothing. All right, so what can we actually do with the model atlas? Well, the atlas enables a variety of tasks, and some of them are what we call meta-ML research, model discovery, model forensics, and many more, but we'll touch upon a few of them throughout this talk. So first of all, meta-ML research. The idea of meta-ML research is the following. We define a recent paper of ours, and the idea is that we want to do sort of sociology of machine learning as a community, sort of understand what different communities do, how do practices evolve and change between communities, and transfer knowledge in order to accelerate research. So let's look at this use case or case study of meta-ML research. What we have here is about 200,000 models from Hugging Face. On the bottom left or bottom right of yours, we can see their legend. So different colors indicate the type of weight transformation. The cyan is adapters, usually LoRa. Greens are full fine-tuning. The pinkish one or oranges are weight merging. This is taking 2 or more models and merging their weights in order to maybe combine their tasks, their capabilities, etc. We also have quantizations, the roots and stuff. And the size indicates a number of monthly downloads. So we can see that we have very popular models, some of them with over 10 million monthly downloads. Because spatial location does not mean anything, I also divided it into different communities. So on the top, we can see computer vision models. On the bottom, we can see the NLP community. On the left, we can see VLM, vision language models. On the right, we can see audio models. And we also have a small cluster of VLAs. These are robotic models, vision language action models. And I also highlighted some of the model names just for convenience. And immediately we can see that there are very different structures and patterns between these communities. So perhaps the most striking one is that now in red, the NLP community uses a lot of model merging. So we don't know why this is. We don't actually know why computer vision doesn't really use them, but we definitely think that we should study it. We think that we should understand how to transfer this thing that looks very successful into our community. Another nice property of the Model Atlas is that we can actually trace the adaptation of technologies. So over here, if we look at markers 1 through 5, and 1 being Stable Diffusion 1.4, 2 being Stable Diffusion 1.5, 3 being Stable Diffusion 2, 4 is Stable Diffusion XL, and 5 is Flux. We can actually see how the community started using more and more LoRa fine-tuning. LoRa's are now marked in red. And we can see that in 1, it's almost completely green, while in 5, it's almost exclusively red. And the hope is that in the future, we'll be able to, using this type of Model Atlas, adapt new technologies, new fine-tuning methods, maybe new optimizer architectures faster, and then propagate it between communities as well. So that was MetaML research. Now let's move on to model discovery. Basically, the idea is that with millions of models available and the expensive cost of training new models, for many use cases that we want to use, we can already take an off-the-shelf model and use it. But the problem is, how do we find them, and are there even good models? And indeed, in a recent paper of ours, we find that there are very good models which no one knows about. So the standard models are usually the foundation models, the most popular ones, but we find that there are very good models which sometimes outperform the popular models by up to sometimes almost 13%. So there are very good models. We call these hidden gems, and that also motivates the use of the Model Atlas for model discovery. So if we already have this Model Atlas, why do we need to chart it? In the beginning, I told you we need to chart the Model Atlas. Well, the answer is we don't really have it. So we have a very small partial view of it, but the documentation for most of the models is missing. And what we actually have is this very partial view of the entire space of the models. So Hugging Face has over 2.5 million models. We're seeing just a very small portion of them which we actually know things about. And indeed, in Hugging Face, we looked at it, and over 60% of the models have no documentation whatsoever, so we know nothing about them. And even from the remaining models, the documentation is very partial. So for example, the accuracy is documented only for 13.4% of the remaining models. And what this means is that most models are essentially lost and effectively unusable. And this prevents all these tasks, the MetaML research, the model discovery, and we don't know what to do with these models. What we actually need is a semantic embedding space of the models themselves, some way to take us from this currently very partial view of the models to the full atlas as we see on the right, our desired objective. And then the question is, how do we learn from millions of models? And the answer is, we view model weights as a new data modality, where each model now is not only a function, but each model is actually a data point, and we can use machine learning to learn on top of these models. And this is all enabled by this idea of weights-based learning, which basically says when we optimize the model, we take the hyperparameters, objective data, we put everything, and it becomes weights after optimization. We then take the weights and upload them into some model repository. And the idea of weights-based learning is that we train these specialized neural networks. We call these meta-networks. These are a new special kind of neural network that takes other neural networks as inputs. It takes their weights as an input, and it tries to predict certain attributes of the Model Atlas, to recover the missing nodes of the Model Atlas, to predict node attributes, predict edge attributes, etc. But weights-based learning is extremely challenging. And the reason is twofold. So first of all, weights are extremely high dimensional. If a standard ImageNet image is about 150,000 parameters, we know that models have millions, billions, and sometimes even trillions nowadays of weights. So we have to deal with high dimensionality. But this problem is even worse because neurons or weights have many symmetries. One of them is permutation and variance. So in the figure here, we can see two identical neural networks where all we did was permute the order of the weights. The functionality does not change at all, but what changes is that the raw representation, if we now flatten the weights, it's vastly different. So you can think of it a bit like processing point clouds with billions or trillions of inputs. So this is very challenging, but in the past few years, we've had a few works in this field, and I'll go over them quickly now. So first of all, we had works on actually recovering the structure of the atlas. So we find that the lineage is encoded within the weights. We can actually do many things from the weights themselves. We have works on recovering pre-trained models from fine-tuned weights. So we get a set of fine-tuned weights, we recover the pre-trained model. We have works on predicting edge attributes, and we actually find that there's a very strong connection between the spectrum of the weights and the number of fine-tuning samples the model was trained on. And we have a set of works on predicting node attributes. We view node attributes, things like the performance of the model or the capability of the models, as essential for model search. That's why we have so many works on that. And indeed, what we do is we kind of optimize these input stimuli to the model. We observe the response, and we can regress, for example, the performance of the model only with weights, no need to use any in-distribution data points. So we regress the performance of the model or predict, for example, the training classes the model was trained on, the functionality of the model, etc. So we've done a fair set of works on this, but there are still many open challenges. So first of all, model weights are still very initial. It's a very initial stage. It's an emerging field, and we need weights priors. So we know about images and text. We know the priors. For example, images are spatially local is important. With weights, you don't know, and we need to explore that. We need new architectures and methods. So our architectures are very preliminary. We view it a bit like early days of computer vision in the sense that we need low-level tasks, we need methods for compression, for doing many things, but we also need self-supervised methods. Our methods are mostly supervised. So self-supervised methods at scale, new architectures, and many new ideas. And finally, a really nice property of the Model Atlas is that basically many of the research field of our community and of different communities can be encoded as node or edge features. So for example, if someone researches robustness, interpretability, etc., they can take the results, add it as another layer of the graph of the Model Atlas, and then slowly we'll build this knowledge about different communities and their results, and hopefully generalize between architectures, between communities, etc. So just to recap, there are now millions of publicly available models, and we need this Model Atlas for a variety of tasks. But in practice, the current atlas is very partial because of missing documentation, and we need methods for weight-based learning to learn from entire model populations. Thanks for listening, and we have the papers, data set, and code on my website, orbits.ai. And yeah, any questions? Sure.
Thanks from linear algebra. What is the rank, the effective rank of all the models? Is it one?
Of all of them together?
Yeah.
It's not one. Actually, it's basically high rank, almost full rank. There are, if you have lower, it's sometimes lower rank and stuff like that. And we have methods that do low rank things as well. But it's not trivial that it'll be low rank. And we're actually working on trying to maybe compress them using low rank things. So for example, if you have all the Flux models, we have about 30,000 LoRa's fine-tuned on Flux, and we do want to find maybe a way to represent them in a lower rank.
And what's the mod?
Yeah.
What's the model that is the most isolated that you've encountered?
Isolated in what sense?
Furthest away from everything else?
There's so many of them. Let's see, there's some models for biology, which is somewhat like kind of niche and stuff like that. I think robotics is still niche, at least on Hugging Face it's now growing. Yeah.
Okay. More questions from the audience? Yeah.
So we don't have methods for actually extracting the data itself. We are working on it. I mean, it's a known task called model inversion, or a simpler version of it is membership inference attack. And we do believe weight-based learning can be very useful for these tasks, but it's not working yet as good as we want it. And for now, we're able to predict the classes. So for example, detect if a model was trained on cats versus dogs or cars versus planes. We can classify between these types of models, but not yet extract actual samples. But we're actively working on it.
Any more questions? Okay, let's thank Eliyahu again.
Thanks.
So this is still a vision conference. The next talk is by Mark Scheinin from Weizmann Institute. And it's learning to see, but somehow we're going to listen to that. So Mark, the floor is yours.
Thanks, Shai. All right. Good morning, everybody. So my name is Mark Scheinin, and I lead the Weizmann Advanced Perception Group at the Weizmann Institute's Computer Science and Math Department. Now, before I tell you about this project, since my lab is relatively new, I want to take a second to introduce you to the type of research that we do in my lab. So at a high level, my lab focuses on computer vision. And by computer vision, I mean perceptual computer vision, where the goal is to understand and model the physical world around us. However, in my lab, instead of using conventional cameras to sense the world, we invent and build entirely new imaging systems that see the world in new ways. And these systems then allow us to understand and model aspects of the physical world that we simply cannot see with conventional cameras or even with our human vision. So today I'll show you one concrete example of what this type of approach allows us to do, and that is inferring the liquid level inside opaque containers remotely without any physical contact and across multiple containers at once. This work was led by my student Matan Kichler in collaboration with Shai Bagon and was recently published at ICCV. Both of them are here, by the way, so you can catch them for questions. So inferring the liquid level of containers can be useful in many real-world applications, like inspecting large warehouses of liquid products, heavy containers that are impractical to put on a scale, and containers with hazardous and radioactive liquids. So how can we possibly tell the liquid content of a container if we cannot look inside it? Well, you'll see in a second that we're going to rely on a different visual signal which we can sense from the outside, and that is the tiny microscopic surface vibrations at the container's surface. Now, we can create these vibrations ourselves using a nearby source like a speaker, but we can also rely on ambient sounds. Either way, you'll see by the end of this talk that our method works for both of these cases. So I'm going to start by giving you some physical intuition about why we can use vibrations to infer the liquid level. Then we're going to talk about how to capture these vibrations using our novel vibration sensing camera. And after that, I'll tell you how we learn to extract the liquid level and container type using our novel vibration transformer architecture. All right, so let's start with some intuition. Now, the intuition for why we can infer the liquid content of a container from its vibrations should be clear to anyone in this room that likes wine, okay? Now, because if you like wine, you probably did this experiment where you fill your cup at different levels, right? And if you give it a little tap, you're going to hear different tones. Now, the reason you hear this nice musical tone is because a wine glass is a very special case where the geometry, the stiffness of the glass, and the liquid level together create this one dominant vibration mode, which is responsible to the tone that you are hearing. However, most everyday containers, like this milk carton, have a much more complex frequency response, which makes the liquid level inference a challenging task. Moreover, some containers even have an insulating layer that creates very similar frequency responses across different field levels. Similar, but not exactly the same. Also, some containers have the same type, but different frequency responses due to small manufacturing differences. Despite these challenges, we show that our vibration transformer can handle all of these cases. Now, before I tell you about this vibration transformer, let me tell you how we capture these tiny vibrations in the first place. So to capture vibrations of an object's surface point, we're going to illuminate that point with a laser. Then, we're going to focus our camera at some distance between the object and the sensor to image the resulting random interference pattern called speckle. And this speckle pattern is highly sensitive to those surface vibrations, which cause it to shift in the image plane. Which means that capturing these vibrations simply becomes a matter of computing those image domain shifts, which all of you know how to do with optical flow and Lucas Canada. By the way, this really cool approach was pioneered by Zev Zalewski from Bar-Ilan University. However, magnifying these tiny vibrations optically, like I've just told you, is only half of the challenge, because we still want to capture them at high speeds to do anything meaningful. Now, in my lab, we are constantly developing novel ways to achieve this type of speckle vibration sensing in practical and efficient ways. For example, a few years back, I've developed a dual shutter camera prototype that uses two slow cameras to capture the speckle shifts at a high speed of 63 kilohertz. And the dual shutter design also allowed us to capture multiple scene points at once, and because we have them at high speeds, we can replay them as audio signals. So for example, here you see the raw input videos of the vibrations of a speaker membrane, and here is the recovered audio from these videos. This is the actual recovered audio. Okay, for now, for our current task, we want to measure many containers at once with multiple points per container. But this type of configuration is not supported by the dual shutter prototype. So we had to invent a new system. Now, in our new system, we use a slightly faster camera to image the defocused 2D speckle grid. But again, at full frame resolution, the camera is just too slow for us. Luckily, this camera allows us to define multiple short regions of interest that intersect our 2D speckle grid. Then, this camera can read out only these regions at the desired high speed. So once we have this high-speed video that subsamples each one of our speckles, we compute the 2D speckle shifts for each point using our custom GPU-implemented method, which you can read about in the paper. Okay. So now that you know how we capture these tiny vibrations, let me describe our vibration transformer, which is the model we've developed to analyze the signals. So for each surface point, the speckle shifts are first converted to Fourier domain magnitudes, which are then tokenized into separate predefined frequency bands. Next, these tokens are fed into a shared point transformer, which analyzes the local frequency spectrum at each of the points. The aggregate token from the point transformer is then fed into a shape transformer, which fuses the information from different surface points. And finally, that class token is used to infer both the container type and the liquid level. So we start from raw vibrations, temporal vibrations. We end up with the information of what container we're looking at and how much liquid it has inside it. Now, during training, we minimize a loss consisting of a soft ordinal loss for the liquid level prediction and a cross entropy loss for the container classification. Okay, so now let's see how we evaluated our approach. So to capture data, we built this really cool rig and capture capture vibration from everyday objects, containers, right? Everything basically we could find for multiple liquid levels while exciting the vibrations using speakers at different locations, playing various audio files. Then we tested our model in 4 validation categories. The first category is containers from our data set, but with new and unseen speaker positions. And this corresponds to tracking some non-disposable containers over time, like those found in factories and offices. In this test, the mean absolute error in the fill level was only 1%, which is pretty cool. The second category is unseen containers whose type exists in our data set. Now, this category is a little harder because of the manufacturing differences between each instance of a container. We also show that our sort loss enables us to get a reasonable prediction for liquid levels that lay in between the levels we had in our training data set, and that our method performs well for ambient sounds, because we work in the Fourier domain. Now, in the paper, we have many additional analyses to answer many questions, like, does our model really generalize? It does. Can we use a simple convolutional network instead of a transformer, and various other questions? Now, you can find the answers to all of these questions in the paper, or if you catch Matan or Shai. Okay, so to conclude, I've shown you a first-of-a-kind method to infer the liquid level of opaque containers remotely without any physical contact using a novel Speckle-based vibration camera. Now, looking forward, we believe that our method opens the door for a wide range of exciting new computer vision tasks, like figuring out the content of closed boxes, detecting spoilage in sealed goods, monitoring agricultural crops, detecting the chemical composition of substances within closed containers, and more and more. However, even more generally, we're interested in the bigger question of what type of hidden properties of the world suddenly become accessible when we look at the world through this new modality of vibrations. And if this type of research interests you too, you are more than welcome to apply and join the lab. Thank you very much for listening, and visit our webpage for some more results. Thank you.
Thanks, Mark. Questions? So let me start with one. Can you detect the material the stuff is made of, the container itself, or the chemical properties of the liquid?
We haven't tried this, but as long as these properties affect the vibrations of the vessel, of the container, then for sure we can solve an inverse problem and probably recover them.
And is there a gauge freedom? I mean,
a
gauge freedom, so you can use different liquids and container material to achieve the same exact vibration?
That's a good question. So there could theoretically be ambiguities between different combinations. However, because we look at a large frequency bands and a number of different points, it is overall very unlikely that the vibrational modes will be exactly the same for these like different materials with different liquids.
Cool, thanks. Questions?
So the scale of data is approximately 5,000 samples. 23 different containers, approximately 5,000 samples. That's a really good question. I would rather answer you offline, but short answer, we are pursuing this direction.
Okay, let's thank Mark again and continue with the next speaker. The next speaker is Omri Eisenkot from Ben Gurion University, and it's the first talk in a long list of diffusion papers from sequences to images. Diffusion foundations for scalable time series modeling.
לא, אין לי סאונד. לא ככה. בסוף עבד. תודה. Hi everyone. It has been a few years since I've been in Vision, so my slides are definitely less visually appealing as the ones before me. But hopefully there's still some interesting stuff for you guys to listen to. My name is Omri. I lead a group at Ben-Gurion University that deals with time series analysis and learning. And the work I would like to present to you today is about generative modeling of time series. This is a joint work with some of my students, as shown below. So to give a bit of motivation, because I believe that most of the crowd are probably less familiar with this type of problem. The idea is as follows. We want to take multiple time series data sets. So time series in general, it's a sequence, and it can be what we call multivariate, which means that it has several channels, and it's very heterogeneous in the sense that it can come from various domains like healthcare, energy, traffic, and so on, and it can present multiple types of information. So the data is typically very noisy, very difficult to handle, and that's essentially the setup. And the goal is to design some method that takes all of this data and learn using it, and then to be able to generate what we call a regular signal. So what I mean by regular is a signal that is being equi-spaced in time, generated, and it is and we can generate as many as we want. So while probably something that might sound weird to you at this point is that people in Vision, for instance, and NLP as well, have been doing this for some time. The time series community, in contrast, is somewhat behind this. So for instance, we are the first to actually work on this particular problem in the sense that we consider working with multiple time series data sets and not only a single one. So really the difference here in comparison to what happened before that is we want to work on many of these data sets. Now, one type of chicken and egg problem of this sort is that if you have a generative model, then you say, yeah, I can generate as many data as I want, right? However, what happens if you have data sets with not so many samples, like very scarce data sets or very noisy data sets that you need to get rid of a lot of the samples? So you cannot really train a generative model to begin with. So the general idea that I will present is basically, how about we take a large corpus of data, train on it, and then we will be able to generalize to multiple new data sets in a few-shot sense. So this is basically just the overview of the project. To kind of get a motivation for why we wanted to do that to begin with, beyond the fact that this was not existent before our work, is the following analysis. What we did is we took some strong time series models at the time, and we benchmarked them with respect to the amount of data that you have for training. So what you see on each of these panels on the x-axis is that we take the full data set and we remove a lot of information from it. So you can see that we train, for instance, for 100%, but then we can also consider only 50 samples. or even more, less than that, only 10 samples. And then we compare the various methods with respect to the performance when they trained only on this small subset. And what you can see in general is that performance deteriorates as you would expect. And this is kind of goes back to the original motivation. What happens if I don't have a lot of data? How can I actually have a generative model to generate that data? So the question is how to actually, resolve this. And as I said, our basic intuition to that is to train on a lot of data, and then hopefully we could do with a few shots, we would be able to generate some new data. The reason, or one of the reasons why I'm here today, is that our solution was based on harnessing a lot of advancements from the vision community. And to do that, I will present briefly some previous work that we had, and it is based on diffusion. Let me just give like 10 seconds on diffusion, because probably many of you know this, but as Shai mentioned, I'm the first diffusion talk today, so it might be nice to give this overview. Essentially, diffusion, it's a process that has two parts. One of them is the forward process, where you take your image, you add noise to it, and the noise can come with many levels up to the point where you get to full noise or white noise. This, of course, depends on the type of noise that you add, but in general. And in the reverse process, what you basically want to do is you want to take your noisy image and then to denoise it. This is typically done using a neural network. The reason why this is a generative model is that if you train this neural network, then during inference, you can take the noise and then denoise it and get potentially a new image. This type of process or this type of model seems to be very effective, both in terms of results and then also in terms of other aspects. And this is what we want to do. We know that vision had very strong models for diffusion and generation, and we wanted to use that. The problem is that we have time series data, and the question is what to do. So the idea is very basic. We take time series, and then we convert it into an image. What I show here is various transforms that you can do to transfer your data. For instance, you can see STFT, which is short time Fourier transform. Essentially, it's a Fourier transform. And it gives you back an image. Once you have that, our model in NeurIPS 24 essentially just took that image and then used plain old diffusion model as if it was a natural image. This tends to work quite well because you don't need to change anything during inference. So for instance, in inference, you can just take a noise and then pass it using a unit or vision transformer, then get back a clean image. The only requirement from this transform I presented back is it needs to be invertible, in the sense that you can take a time series, convert it into an image, and then go back without loss of information. That's essentially it. So we took this architecture and we wanted to now extend it to be able to work with various time series data and various type of channel, number of channels and various type of data sets, distributions, and so on. And this is roughly the architecture. Essentially, the only thing that we needed to change are two components. One, dynamic convolution. This is a very basic building block that takes your image, and if it has a various number of channels, then it essentially uses convolutions on them to fit it into the unit. And we also have a similar building block after the unit, so we are able to map the number of channels to the unit and back. So this is one component. The other component is a data token. So essentially, we train on multiple data sets. So we want to distinguish between them using some type of token. Inference has not changed at all. It just stayed the same. I don't want to go over all of the details for the algorithm, and probably the text is rather small. I just wanted to mention that the main difference with respect to plane diffusion is that we have this dataset token that we take, and then this dataset token is also used during fine-tuning and few-shot adaptation. Some interesting facts about this dynamic convolution. Basically, as I mentioned, it handles inputs and outputs of various channel sizes. It's very basic component. It's just a convolution with some kind of an interpolation. If you're interested, I'll be happy to talk later on. But the benefits of it are actually kind of surprising. Typically, when people want to match between different sizes, they do some kind of padding. However, padding does not scale nicely in terms of compute. So you can see the panel here with the type of G-flops if you have more channels. However, the orange curve, which uses diconvolution, is roughly constant. It's not exactly constant, but it's almost constant. And also, you can see that we gain a lot in terms of performance with respect to the different data set sizes that we actually trained on. The dataset token is also was kind of a nice addition because it allows us to distinguish between different data sets. However, we actually noticed that if we if we fine-tune using the dataset token or without it, the results did not change a lot. It was mostly important for the pre-training phase. I don't have a lot of time, so I just want to mention briefly the results that we have. As said, this is a generative model, so the idea is to take a data set, generate a new one, and then try to evaluate the quality of the data that you generated. There are multiple metrics, very similar to what happens in vision. For instance, context FID is roughly the extension of FID to the sequential case. There are other metrics. I think the main thing that we can learn from this type of table is that our approach works kind of nicely, even at the case where we use all of the data. So you can see that 100% we actually improve on other approaches. But it's also true for the case where we have not a lot of samples, which is the few-shot case, and then we also get some nicer results. Let me skip to the scaling laws. Another type of ablation that we did is we considered models of different sizes from 6 million parameters to roughly 40 million parameters. You can see that scaling laws kind of apply as usual when you have larger models that typically behave better. Right, so just to conclude, one take-home message from this talk is that if you use alternative representations specifically for time series, this could be very beneficial because you can harness other type of architectures to your benefit. Specifically for this talk, we were interested in unified training for scarce data, and this tend to work quite nicely. We have multiple ideas for future work. For instance, I mentioned the transformation from time series to image. This is not learned, and we might want to learn it. And we also want to extend it to multimodal generation when we also include other modalities such as text. I would like to thank you, and I'll be happy to take questions.
Thank you very much. Questions?
Right, thank you. So I was not very rigorous in terms of presenting what the time series to image transformation is actually doing, but essentially it takes each of the channels and transform it into a separate channel in your image. So this is not an RGB image. This is an image with multiple channels. And then it is being fed to a convolution type neural network. So essentially the convolutions, they are both spatial, but they also average information across channels. So I believe, to answer your questions, if there is some kind of knowledge or connections across channels, this will be the place where the neural network will be able to extend those. No, that's correct. So once you have the dynamic convolution, it also applies yet additional convolution. So it might be that some type of connections are more difficult to extract. To be completely honest, we don't have a good test case for this type of data set. So I'm interested if you have some kind of data set that you want to consider. This is not type of an analysis that we explicitly performed. But I see that theoretically, there is definitely the ability to learn from that. But yeah.
Okay. Any more questions?
I'm not sure that I exactly followed. I think your question refers to why apply 2D, why transform the time series to 2D instead of 1D? So the main the main motivation was to use all of the advancements in vision diffusion models where they actually apply to natural image and it works kind of well. That was basically the idea. You can also do something along the lines of what you mentioned. The only thing is that you need to come up with a good architecture that handles this type of information. People have done this in the past. I did not mention them. I'm not against this approach, but this is not exactly on the same type of design that we had.
Okay, let's take one more question, and the next speaker can come up to the stage.
Yes, so, okay, again, I was not very explicit on the type of transform. I probably called it STFT in the slides. It's actually, we take both the phase and we split it both to the real part and the imaginary part. So going back, we can just, convert it without loss of information. Thank you so much.
Okay, thank you. The next talk is an intergalactic collaboration between Bar-Ilan University, Hebrew University, Origin AI, and NVIDIA. The talk will be given by Dvir Samuel, and it's about OmnimatteZero, fast training-free Omnimatte with pre-trained video diffusion models, the second diffusion paper of the day.
Yeah. Okay, so hi everyone. My name is Dvir Samuel, and I'll present our paper OmnimatteZero, a fast training-free Omnimatte with pre-trained video diffusion models. This work is the product of a collaboration between Origin AI, Bar-Ilan University, the Hebrew University, and NVIDIA. So imagine you want to take a character from one video and place them into another. To do this realistically, we first need to solve a fundamental problem, separating the object from its background. This is known as video matting, where we break a video down into a clean background and a foreground layer. A particularly challenging form of video matting is Omnimatte, where we get as input a video and object masks, and output a set of layered videos. First, a clean background layer with all objects and their effects removed, and also multiple foreground layers, one for each object, where each layer includes not just the object itself, but also its effects on the scene. For example, in a video of kids running on the beach, each kid carries their shadow, reflection, and footprints, which need to be separated from the background as part of the Omnimatte. Existing approaches fall into two categories. Optimization-based methods train a small network per video, minimizing reconstruction loss on the input, and thus learn to separate a video into semantic layers. Training-based methods collect datasets of paired videos with and without an object and its effects, and train a diffusion model to erase the object. This produces the background layer. However, they still require extra optimization to recover each foreground layer. Across both approaches, we keep running into the same three issues. First, they are expensive to compute. Optimization-based methods can take hours to just learn the layer decomposition for a single that's only a few seconds long, for a single video that's only a few seconds long. Training-based methods still need hours to train the backbone, plus additional minutes to hours of per video optimization. Second, they are slow at inference time. Rendering can take 3 to 9 seconds per frame, which is far from real time. And finally, they don't generalize well. These methods tend to work only within a narrow setting and often break down on new videos or out of distribution objects. We propose a 3-step end-to-end solution for Omnimatte, which first removes the objects and their effects, then extracts foreground layers, and lastly compose layers together, based only on pre-trained video diffusion models. But the best part is that our approach is training-free, optimization-free, and fast, close to real time. So how did we do it? Since we are aiming for a training-free approach, let me quickly recap how diffusion-based image and painting works without any additional training. Given an image and its mask, say we want to remove the Eiffel Tower. We encode the image and its mask into the latent space of the diffusion model. We identify tokens, latent tokens belonging to the masked region, and replace them with random noise. We then run the diffusion denoising process while preserving the unmasked background tokens. This simple technique works beautifully for images. But if we directly apply this idea to video diffusion models, it breaks. The model removes the object, but replaces it with unstable blobby artifacts. The core issue here is consistency. Image diffusion models mainly need to preserve spatial consistency within a single frame, while video diffusion models must preserve both spatial consistency and temporal consistency. Those extra constraints makes clean object removal much harder, which is why we end up with these unwanted results. We aim to remove the objects and all its effects while preserving the original background over time for the video. Our key insight is to guide the diffusion model at the attention level. First, for each object token, we find background candidates from neighboring frames that can serve as replacements for the object. For example, the dots on the person in the middle frame are matched with the background points from other frames. We then override the attention between object tokens and these background tokens with the mean attention score of background to background pairs. This encourages the model to pull information from consistent background patches across time. We call this temporal attention guidance. Similarly, within a frame, we replace the attention from object tokens to nearby background tokens with the mean spatial background attention, and we call this spatial attention guidance. Together, these two guidance mechanisms enforce both temporal and spatial coherence during generation. To further identify object effects, we observe that these effects naturally appear in the self-attention maps of video diffusion models. We expand the user-provided mask by detecting high correlation regions in the attention maps, effectively capturing all object-related effects. Interestingly, these effects do not appear in image diffusion models. We link this to the common fate principle that says that elements that move together are perceived as one unit, and this is probably what video models seem to learn this idea. The overall pipeline for object removal mirrors the image and painting pipeline. We encode both the video and the mask with a VAE. We replace the object tokens with random noise and run inference using temporal attention guidance and spatial attention guidance. Using our object removal strategy, we generate a high-quality, temporally consistent background video with minimal artifacts. For example, on the top, our method removes the ball in the Find the Ball game that make the woman playing with nothing. On the left, our method cleanly removes the biker and its shadow while preserving the original scene. On the right, it removes the people on the trampoline, including the dent that they leave behind. And at the bottom, the rightmost swan is removed, including its reflection on the water, while the rest of the scene and the other swans are not changed. But the biggest takeaway is this. Compared to existing methods, we are not only improving background preservation, we are also doing it much faster. While prior approaches rely on heavy training and per-video optimization, we achieve state-of-the-art results in real time, with no training and no optimization at all. We evaluated our approach on standard Omnimate benchmarks and compared it with image in painting method, which is simply frame-by-frame in painting, video in painting methods, and Omnimate-based methods. Our approach consistently reaches better quality videos. Here we can visualize these comparisons. Compared to other approaches, OmnimatteZero is able to remove all the target objects, even when there are many of them, like multiple dogs. In contrast, other methods often struggle. They leave behind the dog ghosts or artifacts, remove the dogs only partially or not at all, or sometimes fail completely and output a gray screen. The same effects can be seen in the cat in front of the mirror example at the bottom. Once we obtain the background layer, extracting the foreground is simple. We compute the difference between the original video latents and the background latents. This gives us a full foreground layer without any optimization or extra inference passes. And finally, to compose video layers, we simply add the two latent layers together. To make the blend even cleaner, we run a few quick denoising steps to naturally smooth boundaries and merge effects. For example, it softens the dog's shadow on the grass, and it helps to add details like the car backlights on the water. Thank you for listening. You can find the project page using the link on the left, and we at Origin AI are hiring PhD students and researchers in the link on the right. Thank you.
Thank you, Dvir. Questions? Speak up.
After you remove the objects, like, do you have you thought about like pairing it with some classifier so they can further maybe use this for object identification, or like the joint embedding with architecture, analyze motion, like whether this is following the rules of physics and things like that?
So you mean to take separating the foreground from the background, we just now have the object, we can take it to downstream tasks like classification and so on. It's an interesting idea, but we didn't test that. Yeah.
Speak up.
Does the method work good even when the video is changed frequently, or it works best when the camera is fixed in its position?
So we tested both changing cameras and like stationary cameras, and it actually depends on the model that traces the object during the video. If it works like it identifies the background tokens from other frames, the TAPnet that I presented before, it actually depends on this model, the tracing model. And if it works well, our approach will work well as well.
Any more questions? Okay, let's thank Dvir again.
Thank you.
The next speaker. Hi. Okay, so the next talk is from Ben-Gurion University. It's about FastJAM, a fast joint alignment model for images. And we're almost ready to begin. And bye.
Okay. Sorry about that. לא צריך. כן. מה קורה? Okay, sorry about that. My name is Ron Shapiro-Weber. I'm here to present our work, FastJAM, a fast joint alignment model for images, collaboration with Omri Hirsch, myself, Shira Ifergan, and Oren Freifeld. So, what is joint alignment? Given a set of images, our goal is to find some kind of a common template or an atlas, or sometimes called a canonical space, where all of the images are aligned. This means that given some kind of coordinate in the image, let's say the center of the image, if there's a nose for the sheep or an ear for the horse, then all of them will be in the same XY coordinate. Okay, so let's start with a little bit of background. In the case of image registration between a pair of images, we usually use points of correspondences. The usual recipe is to compute some kind of descriptors, let's say SIFT. We then filter them to find key points or interesting points. We match between them between two images. And finally, we can also compute some kind of geometric transformation, let's say a homography between the images. In the case of joint alignment, our goal is to find a set of parameters, basically one transformation per image, such that all of the images are aligned as a set. More formally speaking, given a set of n images, we want to find a set of invertible transformation. This is in our case. We're going to leverage the invertibility. The transformation are parameterized by theta. So if we have a rotation matrix, then theta will simply be the angle. In homography, we'll have 8 parameters. And we want to find an atlas. Here it's I mu. It could also be thought of as an average of all the entire images. And here we can see we just need to minimize the distance, let's say the Euclidean distance between the mean image and every other image after being warped. Some challenges. The first one is there is no reference image when we're working with a set of images or in the joint alignment setting. So some images can be occluded, some images can only show only one side of the object. So choosing a bad reference can really hinder the process. Second one is that minimizing the variance between the aligned images. So after warping the images, simply taking the variance across the pixel stacks can lead to mode collapse, as we can see here in the animation. So this will bring you zero loss, basically. So you will minimize the loss, the plot will go down, you'll see convergence, you'll be happy, and then you plot the images and you'll see a black screen. Part of it is because of interpolation, but it is something that usually a heavy regularization helps to mitigate. And finally, to mitigate the fact that we don't have a reference and that there are many trivial solutions, many previous works utilize several loss terms, regularization terms, and sometimes even per pixel mapping, sometimes called the dense mapping, which can be very expensive. So if we look at previous works in the field of joint alignment or congealing, we can see that the number of parameters is in the millions. Well, in our work, it's in the bottom row. We only have 13,000 parameters, and the entire optimization process is down from an hour or even 6 minutes, an hour or even 6 minutes to less than 1 minute with FastJAM. So, our framework is generalizing from pairwise matching to global matching or joint alignment. So given a set of 4 images, we can find the matches between the Pekingese, Schnauzer, I'm not sure, the top left dog and all the other dogs. We can do the same for every other image in the set, and then we have key points correspondence between the entire image set. After that, we can build a graph. We build a graph between the pairwise image correspondences, and we add inter-image edges, or within image edges. And then we use a GNN. This is our model. SpaceJAM is a graph convolutional, it's a graph neural network. It's based on a message passing neural network, GraphSage. We optimize the graph for L layers. And then, after during the optimization, we perform image level pooling and linear projection to predict the homography or the warping parameters for each image. So basically, we transfer from a pairwise matching to a graph, we optimize a model, and we predict the parameters for each image such that they are jointly aligned. In terms of loss function, we extend the inverse compositional loss. It's from our previous work by Nir Barel from ECCV, where we warp the I image. We take the I image, we perform the warping, and we perform the inverse of the J image to compare them to each other. So the loss is not computed after alignment, like we saw in the animation where all the images shrink. We compare each image to every other image. So in this case, we take the I image, the blue circle here, perform warping to the shared space, the aligned space, and then we use the inverse of the orange triangle to warp to compute the loss. Our extension is that we perform this loss with key points. This is the same loss, only with key points. We also utilize a robust loss function to avoid outliers, such as the occlusion that we saw or bad matches. And it's very, very fast because we don't need to compute the loss in pixel space or in a high dimensional feature space, such as between dino features. And now that we have some background, we can go over the different joint alignment frameworks, and then we'll move to the results. So most previous models take an image, the model sees a single image at a time, perform some kind of warping to the shared space, and then we compute the loss. In the case of our previous work, FastJAM, again, a single model sees a single image, but the loss is computed in the image space, so there's no risk for trivial solution. And in our case, another contribution is that a single model see the entire image set. So we model the pairwise matches, we build a graph, and only then the model sees the images, so we can model the interaction between the different images during training. Okay, I'm going over some results. So here we can see the visualization of the canonical space. Basically, we take the image, we warp it again to the shared space, we can color it using a splatting, and then we can apply its inverse to color the object. So, as we can see here, you can see that semantically similar object regions have the same colors. So the head of the cat is green, the wings are green and purple, etc. Comparing our model to a visual comparison with ASIC, it's a model from ICCB23. It's performed dense matching, so every single pixel is mapped during the transformation. So we can see it's quite brittle, the source to target alignment here. FastJAM is a previous model, is also good, but not as good because there is no modeling of the only modeling between the entire image set is through the loss, not through the model. And in our case, we can see that the alignment is better and not brittle as all, such as dense pixel matching. Some more visual results. Here in the Seagull's example, we can see that the model can handle large occlusion, as we can see from this example. Many variations in orientation, pose, occlusion, and more. And in terms of results, the standard benchmark for image registration and joint alignment is S-pair. It's one of them. We just measure the percents of pixels between the matched the annotations. So as you can see here, FastJAM achieved the best results. And also in terms of speed, as we saw previously. Accordingly, the slide was also very fast. Are there any questions? Thank you.
Questions? Speak up. Cross category.
Cross category alignment. No.
Dog and a cat. A dog and a cat.
Yeah, dog and a cat. I mean, it should work. It's based on the matcher. We use the aroma for matcher, for anyone who's familiar with. If the eyes and nose and ears will match, then the model will work. How well does it preserve the feature after warping? So we apply an homography transform to the image. So basically, as long as the scaling is not insane, like times 10 or times 100, then it should preserve them pretty well. I think it could be used for face recognition. The standard use case for this model will be to jointly align the entire faces, the entire face collection, and then apply the algorithm.
Any more? Yeah.
Do you have any way to control the position that you get in the joint alignment? For example, nose on the right and tail on the left for all the images to line all the dots?
So can we control the positions after the transformation? So in order to choose a position, you can either use the inverse of one of, like you can use a reference only for the orientation. So you solve the problem for the entire set, and then you choose image B and apply its inverse on the entire aligned collection. So everything will be warped to it. But there's no text or prompt to change the orientation.
One last question while the next speaker is setting up. Oh.
Seems like there's like an implicit tweaking unknown which model behind this transformation that you do. And doing this completely relies on lighting and textures and things like that. I just wonder if there were specific lighting conditions or textures on which your model didn't work as expected.
So I'll just repeat the question. So in terms of lightning, is there any pitfalls or areas where the model doesn't work? I'm not familiar with. We've worked with several benchmarks and several instances. Relies on the matcher. So if the matcher is bad and fails for everything in the collection, then it won't work. But from what I saw, they're pretty robust because the matchers are trained with data annotations, etc.
Okay, let's thank the speaker again. And the next talk is who said neural networks are linear? Asaf will say that. Go ahead.
Hi, so this is a joint work with my really amazing collaborators, Nimrod Berman and Asaf Halak. So we always say that neural networks are nonlinear, but what does linear really mean? So of course it means that it needs to satisfy the superposition principle. But let me just remind you that linearity can only be defined with respect to a pair of vector spaces. So these vector spaces are defined by 4 elements. So these 4 elements are the set of vectors that they act on, the addition and scalar multiplication actions, and the field they're over. And they have to satisfy this long list of 9 or 10 axioms, depending on how you want to count them. And we can't do anything about the set of vectors because this is our data. And personally, I'm too scared to mess with the field. So this leaves us with the vector addition and scalar multiplication actions to deal with. And just, I want you to notice that when we actually write this superposition principle, we have those pluses and dots there. So these belong to the vector spaces. These are the special actions of the vector spaces. And in this work, what we were after is asking the question of what if we can actually find a new pair of vector spaces for which this mapping that we used to call nonlinear is actually going to be linear. So the superposition holds with these newly defined actions. So this is what we term a linearizer, and here is how it works. So if we want to map this non-linear mapping, and we're going to be using invertible neural networks. So for those who don't know, invertible networks is a thing, and there are several ways by which you can implement them. And this is how it's going to work. So we have our input, and we're going to feed it into our first invertible network, Gx. Then we'll just multiply it by a matrix. And then we apply our second invertible network, actually the inverse of this network, Gy, and this is how we get our result. And we're going to train this thing end to end. We're going to train this thing end to end, and all the parameters of the invertible networks and the matrix A are actually learnable parameters. So why are we doing this? What does this structure do? So if you remember, we're after new vector spaces that are defined. Okay, 1 second. Okay. So we are after defining these new vector spaces, and they're defined by this new set of actions. So we need to find what are they. So it's actually very simple. So vector addition in the X domain, for example, what we're going to do, we're going to apply our Gx to both of the vectors. Then we do just regular arithmetic addition of these vectors, and then we apply the inverse of G. And the same fashion goes for multiplication. So whatever you want to do, basically you apply your G, you do whatever it is, and then you go back. You take the inverse of it. So this raises the following question. So first, are these valid vector spaces? And the answer is yes, otherwise I wouldn't be here now. And the second question, does it make F linear? And the answer is yes again, and it's very easy to prove it in several lines. But the point is that this shouldn't even surprise us, because what we were doing here is just this change of coordinates. So we're moving to a coordinates for which our problem becomes linear. So it's a vector space isomorphism. And just as an intuition, you can think about this just like you think of SVD. So when you perform SVD, what you actually do is you shift your problem to the basis for which it is diagonal. So here we use nonlinear transformations to shift our coordinates to the coordinates for which this problem is linear. So the first application that I want to show you is doing one-step flow matching. And the way it's going to work is we're going to do our forward diffusion the way we always do it, but we're always now going to use our newly defined actions. So the definition of xt is going to be just apply g to x0 and x1, do the regular thing, and then apply the inverse of g. And we're going to train our linearizer model to predict the velocity as you do in flow matching. But again, the velocity is defined by the new actions. Now comes the time for sampling. So if we want to perform the sampling, we're going to need taking Euler steps. And it turns out this Euler step in this formulation is actually also linear, again, over the newly defined vector spaces. So since it is linear, we can actually express it as a linearizer again. And now, if we want to actually generate images, we will need to sample all the way. We need this sequence of Euler steps. And I think some of you already know what's going to happen here, because when you take a sequence of linear operations, they become a single one. Okay, this has to collapse. And we're going to see it happening, because if we look at those G inverses and Gs all over this sequence of linearizers, we know that just like when you diagonalize matrices and stuff like this, they're going to die together. And we're going to have this sequence just of linear matrices. And then this multiplication of matrices becomes this one single matrix. So yes, it's an ugly matrix. but it's our ugly matrix. And here's the nice thing is that you only have to calculate it once. Okay, you call this thing B, you finish your training, you do this multiplication of matrices, you save it, you forget about it, all you remember is that you have this B and you have your one-step sampling. And here is another intuition that I want to share regarding this. So think about this diffusion route, this flow matching route that you're now taking. What we were actually doing when we were training this end-to-end is we were searching for the space for which this line, this curved line that you're seeing now, is a geodesic. Okay, this is what we're looking for. In other words, our G transforms the entire space so that the problem, the curve that used to not be linear, then becomes linear, and we can think of this optimal transport path that we're taking as a geodesic of it. So it's only a straight line in the induced space. And you can see we have some MNIST and Celeb A results, and we can do this latent space interpolation since it's only a one-step thing. But an important thing to notice here is that if you look at the multi-step result and the one-step result, they are identical. So there is no distillation here or anything like this. It's, what you're seeing is just mathematically equivalent. So the elephant in the room usually is the expressiveness. And the question is, can you linearize anything? Can you express any nonlinear function using this sandwiching with invertible networks? And I'm happy to say that the answer is no, because you can think of a very simple example, and this is the fact that linear functions, their null spaces, they only have two choices. They either have one vector in the null space, which is the zero vector, or they have infinitely many, a space of these vectors. So for example, a nonlinear mapping that has two zeroizers cannot be linearized. However, we need to think of the practical world. And we know that all the problems we always want to solve, and especially in computer vision, the data that we're using is on this manifold with much lower dimension of the space that we're working in. So for example, the manifold of natural images is a tiny subset of the entire space. So practically, this is what can happen. So if I have a mapping that only has two zeroizers, it has two zeroizers in the data manifold. So what I can actually do is throw all the garbage out to this huge degree of freedom that I have outside of the data. And what you see here is this curve, this is the null space, and these two zeroizers are on the data. And moreover, and this is thanks to our gracious reviewers, we had to, and we did this at some point, make a proof showing that for any finite data set, we can fit a linearizer, okay? But I don't want to imply that everything is perfect and easy. The real challenge is the optimization. So optimizing invertible neural networks is notoriously hard. So it's challenging. It works, but it's challenging. So, okay, here's another application. And this is the applications for perfect idempotency. So an idempotent function is this function that you apply once and something happens. And then when you apply it again, nothing happens. And most of us are familiar with the linear case, which is projection matrices, when A squared equals A. And some weird people in the past have used it for generative models. And it turns out, luckily, that if we take the inside A of the linearizer, and if we make it a projection matrix, then it means the entire linearizer is actually idempotent. And the important fact about projection matrices is that all their eigenvalues can only be either 1 or 0. And this is the trick that we're going to be using now. So what we want for a perfectly idempotent neural network is to is to make the eigenvalues of A ones and zeros. And to get that in a way that is differentiable, we're going to use this straight-through estimator, and we'll have these two losses. One loss is we want to be able to reconstruct the data, and the other is we want this matrix A to be as sparse as possible. So more zeros, less ones. We want to tighten it, so only the real data passes through. Now, we can see the generative model works, so we have noise in and data out. But the thing is that it is a global projector. So this can work on many other types of things. So for example, whether it's noisy or blurry, or this thing you can call a rested digit, and they all are just projected back onto the data manifold, and this also applies to anything else. So this is a truly global projector. Whatever you put in, it's going to be projected onto the data manifold. So, yeah, thank you. And we have some other applications that you can check out in the paper for modular style transfer and the nonlinear pseudo-inverse. And I'm happy to take questions now.
I'm glad I have this effect. Thank you very much. Questions?
How is this different from the rectifier that train and rectified flow models?
I'm not sure how it's different because I'm not sure why it should be the same.
In both cases, you train an additional model that aims to make a single step, like the multi-step diffusion to a single step. Here you train the linearizer. You train it, right?
It's what?
You train the linearizer.
Yes.
And in rectified flows, you train the reflow model. Are they like similar in essence or practically?
No, no. So not really. They're not very, it's not quite the same because here you have the model that is linear, and then what you do, you turn the entire problem to be linear, and then it just mathematically collapses to just a single step. Okay.
Additional questions? Okay, thank you very much, Asa.
Thank you.
And the last talk for this session is from the Technion. It's about from in-painting to pathways, a temporal approach to image manipulation.
לא, רגע. אתה יודע איך עושים את המסך כפול? כפול? כאילו שרואים שני מסכים.
זה אמור להיות אוטומטי.
כן.
תצא רגע. תפתח את פאורפוינט, תפתח את זה.
כן, לא יודע למה. לא רואה פה את ה...
אולי יש לך עוד... אז עכשיו לא אכפת, עכשיו תעלל.
הנה, סבבה. So, hi everyone, my name is Noam Rothstein. I'm currently a PhD student at the Technion under the supervision of Ron Kimmel. Today I'll be presenting my talk from static in painting to dynamic pathways, a temporal approach to visual manipulation. I'll be covering two papers from the last CVPR. Both tackle image manipulation, but we also demonstrate potential and adaptability to other tasks. So this leads us to the first paper, Paint by Paint, learning to add image objects by removing them first. This is a joint work with Nave Wasserman, Roy Gantz, and Ron Kimmel. So in this work, we tackle the task of adding new objects to images. Let's look at a concrete example. Here we have Messi, moments after winning the World Cup. Of course, we are all happy he finally won. So we want to celebrate by adding the king's cape to him, using nothing but a simple text instruction. Unlike text-only condition generation, editing requires adding an object while maintaining maximal source consistency. For example, in this edit, the identity background and pose must be preserved. So image editing can be generally split into two main approaches. The first is mask-based in painting. In this setup, we provide the model with an input image and a corresponding mask. The model is strictly constrained. The edit is performed only within the mask boundaries while maintaining consistency elsewhere. So this setup is especially straightforward and effective to train because any image can be used as training data. For example, given this image, we simply mask the flower, and just like that, we have a valid input and target pair. We then train a diffusion model to regenerate the flower. The model learns to reconstruct the missing pixels from noise, conditioned, and the masked image we just created. Where text conditioning can also be used as an additional control signal, and due to this availability of an infinite amount of data, mask-based in painting is highly effective. But what happens when you don't have a mask and you want to drive the edit using only text? So unlike in painting, for this task there is no available pair data. This has made mask-free image editing a highly active domain with many different types of solutions. So for example, let's take instruct pix to pix. This model, which was a leading editing approach at the time of its release, bypassed the lack of real paired examples by training on fully synthetic data. However, if we examine the dataset, we often see significant source-target consistency issues. For example, look at this image pair. The instruction is add a giant spider. While the paired image correctly contains the spider, it also incorrectly modified the background. The house is different, the trees have become snowy, and in general, the scene integrity is compromised. This data inconsistency directly degrades the post-training model performance, motivating us to build a large-scale, consistent editing dataset for object addition. So in this paper, our key insight for building such a dataset is that given a highly effective in-painting model, removing objects is significantly simpler than the inverse process of adding them. Because adding an object requires us to provide a segmentation mask for where that object would be, essentially requiring us to hallucinate the shape and position of the mask. In contrast, for removing an existing object, the mask is already latent in the image and can be easily extracted. This implies that this approach is highly scalable. Given a large-scale segmentation dataset, we can easily construct training pairs automatically. Finally, we can use these generated pairs to train a diffusion model to invert the in-painting process. By learning this reverse mapping, the model effectively gains the capability to add objects to images without using input masks. So in-painting models are not explicitly trained for removal, so we apply numerous filtering techniques to strictly verify the outcome. And in addition, we synthesize instruction in various styles to ensure the model can handle diverse human-like phrasing. The outcome of these steps is PIPE, an object addition dataset of approximately 1 million images. Unlike previous datasets, our target images are natural, not synthetics, and source target consistency is maintained by construction. Training on PIPE results in a model that is highly effective at adding objects, surpassing any available model at the time of its release. So this work led us to a new question. We can now add objects to images, but can we perform more general editing, such as object replacement or complex non-rigid transformations? To answer this, we present our next paper, Pathways on the Image Manifold, Image Editing via Video Generation. This work is joined with Galiona, Daniel Silver, Roy Velitz, David Ben Said, and Ron Kimmel. So in this work, we approach the problem from a geometric perspective by simulating the image manifold. To do this, we generate 3 distinct groups of images. People with AI on their shirts, people making a heart shape with their hands, and finally, people with a combination of the two. We then take all these images, along with pure noise, and perform dimensionality reduction using a clip image encoder and PCA. We project the data down to 2 dimensions. This results in a clearly defined 2D manifold distinct from the noise samples. We see clear clusters for each group, where notably the combined group in purple lies geometrically between the AI cluster in green and the heart-shaped cluster in red. Now, returning to the challenge of editing, let's examine this input image, a person wearing a shirt with the text AI, which is mapped correctly to the green cluster. If we attempt to edit him to make a heart shape using Ledits++, a leading editing model, we see an issue. While we do get the heart shape, the result overshoots the red cluster, and this means the AI is lost, signifying a failure in source consistency. Our goal is to maintain the AI, which geometrically means landing in the purple cluster. The way we achieve this is through incremental semantic changes, slowly moving on the manifold. And we do this through video generation. So video generation has seen massive surge in interest in recent years. At the time of our work, Cog Video X was the open source state of the art and the model we used in our experiments. Video models operate similarly to image models, but instead of a single image, they denoise sequences of noisy frames. A popular variant involves image-to-video models. In this case, the video generation is conditioned on the first frame and not just the text prompt. We adapt this model to perform editing. We define the source image as the initial frame, and then generate a video that creates the desired manifold edit pathway. We need to take 2 factors into account. First, standard editing models typically expect a target image caption as their input prompt. However, we need to explicitly describe the temporal changes required for the video generation. We term this modify input as temporal editing caption. The second factor is that video models output a sequence of frames rather than a single output image. Since these models tend to deviate from the source over time, we select the first frame that satisfies the intended edit. Putting it all together, we present frame to frame. We start with an input image and a target text prompt. We construct a temporal editing caption. We then feed this caption along with the source image into an image-to-video model to generate the sequence. And finally, we select the specific frame that achieves the desired edit. To get a fully automatic process, we automate both the temporal editing caption and the frame selection using vision language models. One of the nice aspects of this method is that we can observe how the semantic edit is performed. Take, for example, a tennis ball transforming into a tomato. The model might achieve this by having a tomato simply land on top, or by synthesizing a hand, sometimes deformed, to replace the object, or by directly and gradually warping and morphing the ball itself. So going back to the manifold, we can see we get exactly what we wanted. We output an edited image that maintains consistency with the source, successfully ending in the purple cluster. So frame to frame performs different types of edits, all without any training. It outperformed all competing models at the time, achieving the same target clip score, matching the editing quality while maintaining higher consistency with the original image. This led us to the question, if we can reformulate image editing as a temporal process with incremental frame changes, can we apply this logic to other tasks as well? We demonstrate this approach can be applied to tasks such as denoising, deblurring, outpainting, and relighting. These ideas are now beginning to take hold. Recently, a popular paper from Google adopted a similar framework. They reframed the manifold pathway as a form of visual reasoning. Beyond showing improvement on the task we demonstrated using the powerful VO3 model, they introduced new tasks such as maze solving. We believe our work opens up exciting avenues for future research, suggesting a shift where video models evolve from content creators into tools for visual logic and problem solving. Thank you.
Thank you very much. Questions? So one question is, there is a shift now to robotics. Can you help in that domain? Do you see any possible use cases where robotics will benefit from this new representation?
Can you elaborate what you mean? Like which kind
So
of...
you have these pathways and you can generate all possible scenarios essentially. So you can train an autonomous vehicle, you can train a robot to encounter all different possibilities without actually going through them. Have you looked into this direction?
We haven't specifically done that, but I think we see as the video models get more powerful, they become more useful for many tasks. So I guess it's a promising direction.
Any other questions? Okay, let's thank all the speakers of this session. We'll take a break now, and we'll reconvene at 11:15. 11:15, and just a reminder, no food or beverage inside the hall. Thank you.
talk in this session will be by Roman from Weizmann.
Hello, everyone. I will be presenting our latest work, BrainIt, image reconstruction from brain activity. This is a joint work with Amit Zalcher, Jonathan Kogman, Naver Wasserman, and we are all from Michal Irani's group from the Weizmann Institute. So when a person sees an image, there are billions of neurons firing in every moment, but we can't actually measure all of them. And we don't, but what we can do is we can put the person inside an MRI machine, and in the MRI machine we can measure the fMRI signal. In the fMRI signal we measure the brain activity indirectly, and we get a measurement. We divide the brain into 3D voxels. Each one is of size millimeter cube and has around 100,000 neurons. And we get their average energy consumption. So for each image, we can get the brain activity in different regions with a high resolution. Now, the setting that we work with, that we have a person that views images inside the MRI machine. We have here the fMRI signal, and from the fMRI signal, we would like to get back the image the person is seeing as accurately as possible and closest to the original image. Now, why is this task interesting? So first of all, it's a way to understand the brain, how the brain processes and visualizes visual information. Second, it's an application of this is a computer, the brain-computer interface. Imagine we have a locked-in patient that can't communicate, so we can establish a communication channel with him with this kind of techniques. And finally, it's a window to consciousness. It will allow us in the future to visualize memories and dreams. Why is it challenging? So first of all, the signal is very noisy. Usually we have very limited data per subject, as gathering the data requires the person to be physically inside the machine. And combining measurements from different people is not trivial, because every brain is different, so we need our model to somehow to accommodate for this. So let's go over our approach. So we said that we want to reconstruct an image. So we know today that the most powerful tool for image reconstruction is diffusion models. Now, we don't just want to generate a random image of a cat. We want to generate an image that is related to what the person is actually seeing. So we want to condition the diffusion model on some semantic features. So here we try to start from clip tokens, from positional clip tokens, and from them to reconstruct the image, but we don't actually have them, so we need to predict them. So what we do, we take the fMRI signal. We have a model with a transformer that we call brain interaction transformer, or shortly BIT, that predicts these features, and these features condition the diffusion model, and we train everything end to end. So from the fMRI signal to be able to reconstruct the image the person is seeing. Now this works well, but it fails to capture the structure of the image and details. So what we can do is not start just from noise, as usually done with diffusion models. We can start with some low level or structural image. And then it means we don't start the diffusion model from noise. We start somewhere in the middle, and then we have this refinement of the image with the semantic conditioning. Now, how do we get this image? Because we also don't have it. So what we do, we take visual features. In this case, it's VGG features that were trained on ImageNet, so it's convolutional features. We predict them, and then we invert them to get this low-level image, and this is proven to be much more stable than transformer-based architectures. Okay, so now we need some background on how the brain actually represents visual information, and this will be guiding principles for our model. So one thing that we know that we have spatial organization in the brain. What do I mean by that? So here we can see the left side of the image will be mapped to the right hemisphere, and it will be distorted in this very particular way where different locations in the brain will process specific location of the image. So we have this retinotopic mapping. This is something that is known from studies in neuroscience. And another thing that is well known and well established is that we have specialized processing. We have different regions in the brain that do some specialized function. So we have an area that is responsible for processing faces, places, objects, and so on. And all these regions are also interconnected. So each one of them affect each other, and together they create perception. Now let's talk about how we take the fMRI signal and using a bit produce the image features. So it's a two-step process. We start from the brain voxels, and we have around 40,000 voxels per person. We then transform them to something that we call brain tokens, that I will shortly explain what it exactly means. So we transform them to 128 brain tokens, and these brain tokens finally we transform to localized image features. So let's focus on the first part. How do we take the brain voxels and transform them to brain tokens? So we take voxels of multiple people, and we cluster them according to functional embedding that we learn. And this is a bit similar to what we saw before of specialized processing that we have the brain. So we basically infer in a data-driven way specialized groupings of voxels. Now we want to transform these voxels to brain tokens. So this mapping, this clustering define the mapping, and we can use this mapping in a graph attention network to take and summarize the information in each group of voxels to a brain token. Now we take the brain tokens that we just calculated, and we put them inside a transformer. In the transformer, using self-attention, the brain tokens communicate with each other, they refine each other representation, and get a better representation. In parallel, we have query tokens that aim to extract the localized image features that we need in the end to reconstruct the image. This is done with cross attention, and each query token is responsible for a different position in the image. And this happens in parallel. And this special localization is similar to what we saw in the organization of the brain with localized processing. Let's look at our results. So on the left, we see the image the person actually saw, and on the right, the image that we are able to reconstruct with our model. So we can look at some examples. So here we can have a surfer. So we can see that we are able to reconstruct the surfer in the position. So it's not exactly the same, but it's very similar. Here we can see a snowboarder. So we are able to reconstruct the snowboarder, the position of the hands. Here we have the three skiers. So we are able to reconstruct the semantics of the scene and the position of the skiers. Here we see the motorbike. So the color are not exactly the same, but we can see the position of the bike and the background. And here we can see the picture with the position of the hands and the legs. So we can see that we are able, from this fMRI signal, to get back a lot of the information of the image, both semantics and the structure of the image. So now maybe it's a very easy task. So let's see how our competition does. So here we compare to the leading methods. So here you can see the image with the horse and the sledge. So we are able to reconstruct a horse with a chariot, and we see that our competition usually fails completely. Another example is this hotel room. So we can see that we are able to reconstruct the bed, the linings, and our competition only can get roughly that it's a hotel room with no details whatsoever. Let's also see our failure cases. So here we can see the failure cases. So this image of the cake, okay, so we can't reconstruct exactly the image of the cake. We get hamburgers instead, but we can still get the overall structure. Another example is this dog in a bathtub. So we get a goat instead. Let's summarize. So we demonstrated high fidelity image reconstruction from fMRI. And what are exciting future directions? So first of all, now we are able to investigate visual processing pathway in the brain and understand better how the brain processes and represents visual information. Another thing that we do is analyze individual differences in perception and better study how it relates to other human behavior. And finally, study and understand better neurodivergencies to see how people with autism or ADHD, how they perceive things, and also study different conditions like PTSD and hopefully aid in some therapeutic procedures. So, thank you.
Thank you. Any questions?
So in the experiment, the people are told to focus in the center of the image all the time. So this is what gets the alignment more or less. And also with the VGG features that we predict, we are able to get a lot of the overall structure of the image. So this is how we get the alignment and why it's present in the data. No, it's completely different images. So the VGG we take pre-trained that was trained on ImageNet, and the data that with fMRI is built on top of COCO. So it's very different kind of images.
Okay. Yes, please.
How much variation do you get across different people?
So there is a lot of variation people in terms of quality of reconstruction. So there is a variation there, and generally there is difference because it's a diffusion model. You have some variability just because of seeds, and also there is variance between people.
Okay. One last question.
So in this data set, we have 8 people. Each of them have seen 10,000 different images. So overall, there are around 80,000 images in the whole data set that we train on. And it's around, in terms of fMRI, it's 40 hours of recording. So it's a huge data set. 40 hours per person.
Okay, thank you. Let's thank the speaker again. Sorry. Okay, so our next speaker is Shimon Malnik from Tel Aviv University.
Hi, everyone. My name is Shimon Malnik. I'm a PhD student here at Tel Aviv University. I'm co-advised by Professor Shai Avidan and Professor Ohad Fried. And today I'll present our work, Memories of Forgotten Concepts, together with Matan Osanovsky and Amir Yevnisek. And our work deals with the concept erasure and diffusion models, which means denying the generation of images depicting some concepts. Our focus will be an evaluation of these types of models, and we'll actually ask whether such models truly erase concepts. So a small recap on diffusion models. In diffusion models, what we care about is that we start from a random latent seed that is drawn from a standard normal distribution. And we also start from some prompt that we want that describes the image that we want to generate. We feed those to a diffusion model, and we can generate some image. And if we use different latent seeds, so we'll get a different image that is still aligned with the text that we got given. And when we talk about concept erasure, we need to remember that these diffusion models were trained on very large-scale data sets, and mostly a lot of them were heavily web scraped, and that means we have a lot of unwanted data inside them. So one good example for that is violent data. So in the prompt we see here, we have some violence, and if we feed it to a vanilla diffusion model, we'll get a violent image. And a lot of the time that's unwanted. So that is where concept erasure comes in, and the focus of works in that field is to actually fine-tune the model so that when you give, again, prompts that describe that violence or that concept in general, you'll get images that are considered safe in that sense. And what we care about is to actually ask, how do we really know that the concept is really removed? Because we only talked about the link here between the text and the model. And just to frame our work, so we evaluate these concept erasure models. I will not show a new fine-tuning scheme to fine-tune diffusion models for concept erasure. What I will show is a new paradigm to how to actually evaluate whether we perform a forgetting or erasure. So let's talk about the standard evaluation that we have for these types of models. We usually take text prompts from the concept that the model has actually erased, and we check whether the model generates images with that bad concept. So here in this example, we see the model failed because we still see violence in the image. And we can see another example where the model succeeds because we don't see a tank in the output. But again, what we care about is to understand whether the model actually scrubbed away all that data about the concept. And this is exactly where we step in. And I'll show a series of 3 questions along the slides. And the first question is, can we actually recover an erased concept from an ablated model, which means a model that erased some concept. So our key observation is that we are able to do that, and we think of the problem in the opposite direction. So instead of starting from a text that leads to the generation of some bad concept, we actually start from an image that has a bad concept, and it's easy for us to acquire those now that we have a lot of generative models. And we use the big tool of image inversion, of diffusion inversion, to reconstruct, to acquire a latent seed that can be used for generation for an image that looks practically almost the same, but very similar to the image we started with. And here are another couple of examples of these types of our reconstructions. So for the concept of Van Gogh, if we start from an image, and we can see our inversion reconstruction is with very high quality. And here's another example for the concept of church. And now we know about our first question, that we indeed can find, we call them memories of erased concepts, because we found latents that can lead to the generation of those bad concepts. And our second question is because we know that diffusion inversion is a very powerful tool, and it can invert a lot of images and give us a latents that can be used for generation. We want to understand how likely are the latents that we got for generation. Because if what I showed you lead to some latents that are very far-fetched in the latent space, and that a user that will use a diffusion model will very unlikely, a user will never encounter such a latent, then it's the case is a bit weaker. So we want to quantify the likelihood of encountering such latents. And that's what I'll do next. So to do that, we devise a new distance metric that goes as follows. We start with the images that depict the bad concept that the model, again, was supposed to erase, as we saw before. And we take those images, we invert them, and we have latents in the latent space that can be used for the generation of those concepts. And we gather all these together, we fit a Gaussian distribution from their likelihood, or negative log likelihood, NLL for short. So we fit a distribution from all of those. And we want to compare this distribution to the distribution of random normal latents. Because again, this is a prior distribution for generation in diffusion models. We start from standard normal Gaussian noise. And we also care about reference images, or images from concepts that we didn't intend to erase. We care about those because we want to see that the model's generation is intact, and the model can still generate very high quality images that are from all of the world except for the erased concepts. So we do the same for the reference latents, and we compare those distances. And our goal for the bottom part for the reference latents, we want this distance to be as close as possible. Again, that will help us quantify how the model can still generate images that are not from the erase set. And for the top part, we want the opposite. As I said before, we want to push away the likelihood of encountering such latents in the space. We use Earth mover's distance for our metric. And just for the results that I'll show next, I'll say that a higher score of that metric means a better erasure. So let's see a bit of results that we evaluated across different erasure methods and across different concepts. So if we take a look here, we see the best, again, higher is better. So the best score is achieved using a model called ESD, Erasing Stable Diffusion, on the concept of a parachute. We see we get a score of 2.49. And if you take a look on the distributions I showed before, we have here in green the random normal latents, and we have in yellow the reference set. And we see there's a big overlap between the distributions of the reference set and of the erased concept latents. So that is not an optimal situation for us. It means for us that we can still generate a lot of the erased concepts, although erasure was already been applied to the model. Again, it's a fine-tuned model that was supposed to erase that concept of a parachute. For us, we think something like this, like the blue curve, that would be a better erasure because we were able to kick away those erased latents without any overlap to general images. So this is for our second question. We saw that we can find a lot of, not a lot, but erased concepts that are likely as reference latents. And for our third and last question, we want to ask how many of those we can find. So we started off by just reconstructing some image, and then we wanted to see that the reconstruction is actually plausible and we care about it. And now we want to even extend a bit more the notion of forgetness and to understand whether it's something very local in the latent space, like we can just surgically come and scrub it away, or it's something that is much more bigger, and we can find latents that can lead to the erased images in all over the latent space and in different places. And that's what we'll do next. And we'll even focus just on one image, not an entire concept, just trying to analyze one image. So the way we do that is we start from an image here. We talk about the concept of Van Gogh, and we take that image, and we use diffusion inversion, and we find a latent in the space that can be used to generate that image or a very similar image. And using different initialization that we came up with, we're able to find different latents in different areas in the latent space that can lead to generating a very similar image. And we actually care about the distance of those latents in the space. So we measure the pairwise distance among these different latents. And we try to find the maximum value of maximum number of latents we can find in the space. So because of computational complexity, we stopped with 1,000, but we did it for 1,000 different latents. And we found that the minimal cosine distance between pairs is at least 0.56. Which is big enough, but the point is that it's not a lot of latents that we found just in a specific area with a small cosine distance. It's actually a lot of different areas in the latent space. So for this last questions, we see that there are at least 1,000 memories and probably more for a single image. And before I finish, I want to leave with an open question to show a bit of the power of diffusion inversion. But if we take an image of a church, as I showed before, and we shuffle its patches, and then we took a model that erased the concept of a church, so it's not supposed to know what it is and to learn how to know how to generate it, and we performed image inversion on the shuffled patches, and we got this image of the shuffled patches. And then when we deshuffle the patches back, we get an image that, while the reconstruction error is not amazing, but we can all, I hope, see the church here in the image. And it shows us the true power of diffusion inversion, and that even images that were not part of the diffusion training process, such as the shuffled patches, we're still able to perform an inversion and see and get a high reconstruction rate for these kind of images. So to conclude, I'll just go over the three questions that I gave. So we asked whether we can recover an erased concept from an ablated model, and we saw that we can. And we saw that we can find memories as such that are also likely, and we can encounter when we generate. And we also saw that there are many memories of those in the space, a lot, at least 1,000 that are distant from each other. Please check our project page and code, and thank you very much.
Thank you. Any questions? Yes? Just speak up.
So the example I gave is synthetic, but what we showed is we actually benchmarked all the current erasure methods, and we saw like where we stand. But maybe I agree with you. What the example that I showed maybe is a bit too much. But the point is to try to push that boundary to more to the extreme. And we haven't done an experiment, as you said, but I think it's very interesting. And I think our main focus is just to say that now ahead, when we proceed with concept erasure, we want to also care about the likelihood and not just about the link between the text and the generation, because that's what where evaluation were until now.
Thank you. More questions? Yes, please. Can you just speak up?
Yeah, so in question 2, we did the metric, we used even we used different images for the concept. So we have a concept of violence, and then we took a lot of images of violence, and that's how we collected a lot of the erased latents. And we also always compared it to a closed set of images from MS Coco as reference latents, but we didn't perform just for the specific image, as I showed before. So it's a different part of it.
Okay, thank you. Let's thank the speaker. So our next speaker is Yoni Slutsky from Tel Aviv University.
Okay, so hello everyone. Thank you for having me. My name is Jonathan Slutsky. I'm a PhD student at the Foundations of Deep Learning Lab here at Tel Aviv University. Today I'll be presenting our recent work, the implicit bias of structured state-space models can be poisoned with clean labels. It was done with these great collaborators, and it was recently featured as a spotlight presentation at NeurIPS. So what are structured state-space models? Well, structured state-space models, or SSMs for short, are sequence-to-sequence models underlying some prominent neural networks, including S4 and Mamba. And they are considered somewhat efficient alternatives to other state-of-the-art models, including transformer-based ones. Specifically, SSM-based models are considered competitive in a wide array of vision tasks, including segmentation, video understanding, and also medical data. Our interest lies in the implicit bias of gradient descent when training SSMs, which deals with the following phenomena, which is widely spread in deep learning, in which with various deep learning models, optimizing via gradient descent often leads to generalization, even when the model size is much greater than the training set size, and when there is no explicit regularization of the trained models. These two facts mean that multiple models exist that fit the training data, some generalize while others overfit, and gradient descent somehow finds those that generalize. The conventional wisdom on why this happens is that gradient descent induces some implicit bias towards those generalizing mappings. Intuitively, there exists many solutions that fit the training data. Some are very complex and overfit it, while others are more simple and generalize, and gradient descent has some bias to find those generalizing more simple solutions. Our goal in this work was to theoretically analyze the implicit bias of gradient descent when training SSMs. We consider the following basic setup, where we have single input, single output linear dynamical systems with diagonal transition matrices. The parameters of our models are as follows. We have A, a diagonal transition matrix, B, an input matrix, and C, an output matrix. And the dynamics of our models are as follows. For any time step h, the current state xh is multiplied by the matrix A. The current input, u of h, is multiplied by the matrix B, and together they bring forth the next state, xh plus 1. As for the output, this one, yh, is given by taking the current state, x of h, and multiplying it by the matrix C. We considered the following teacher-student learning scenario, where we have some unknown teacher SSM with parameters A star, B star, and C star, and we are given a pre-recorded training set of horizon capital H, we denoted by the letter T, and it consists of pairs where the first element of each pair is an input sequence of length capital H, and the second element of each pair is the output at time h of the teacher under the respective input sequence. Our goal is to learn a mapping that fits the teacher SSM up to any horizon, that is the horizon seen in training, but also to longer horizons not seen in training. Our method of doing so is training an overparameterized student with parameters A, B, and C, all of dimension D greater than the dimension of the teacher and the horizon in training. We train this student via gradient descent over the mean square error objective, where the labels we consider are the outputs at time h of the student SSM under the respective inputs. Our first result is a dynamical analysis of gradient descent when training, which reveals a property of the models that gradient descent tends to find. We first define an input sequence as a special input sequence when its last two elements are relatively large. Our first proposition states that when learning the student SSM via gradient descent, all of the input sequences are not special, that is, their last two elements are relatively small, if and only if the learned matrix A exhibits greedy low-rank learning, that is, the matrix A is learned such that it has the minimal rank possible subject to fitting the training data. The reason this property is of interest is because this is a sufficient condition for generalization of the student when the ground truth, that is the teacher, is of low dimension. So the main takeaway of our first result is that no special input sequences in the data means that A exhibits greedy low-rank learning. We verify this through experiments where we train SSMs first without any special input sequences in the training data and then with them included. And indeed, we see this phenomena exhibited when plotting the entries of A throughout training. We also see that this phenomena extends to SSMs when they are embedded into nonlinear neural networks as layers. The second result, which is a surprising consequence of the first result, has to do with the generalization of the trained models, where we see that cleanly labeled special training examples can negatively affect the generalization of the models. We have the following theorem, which states that under some technical conditions, for any horizon, capital H prime, larger than the horizon in training, there exists a training set T without any special input sequences, a special input sequence U dagger with a label Y dagger generated by the teacher SSM. So this is a clean label, correctly labeled by the teacher, such that when we learn the student SSM via gradient descent, generalization to horizon capital H prime takes place if we use T on its own, but does not take place if this special training example is appended to T. The situation we have here is a situation where we take a model, we train it on a base data set, and the model generalizes. Then we take the same model using the same algorithm, the same initialization, and so on. But instead of taking the original training set, we take an extended training set, all consisting of correctly labeled examples. So this data set contains more correct information. And instead of generalizing like we intuitively expect, this model now overfits the training set. This is a phenomena known in the adversarial machine learning community as clean label poisoning. So this theorem establishes that SSMs are susceptible to clean label poisoning. We verify this phenomena in experiments, first in a synthetic experiment where we train various SSMs, first without any special input sequences, and then with them appended to the training set. And indeed, we see a drop in performance. And here too, this phenomena extends to SSMs in nonlinear neural networks. And we also have a real-world experiment where we train SSM-based neural networks, including S4 and Mamba, on the CIFAR10 dataset. Here, instead of having special input sequences, we have poisoned input images, which are images to which we added some imperceptible noise in the structure that is suggested by our theory. This noise is imperceptible, so the original CIFAR10 labels remain valid. And indeed, here we also see this drop in performance, even though we added correctly labeled data. So let's recap. SSMs are efficient state-of-the-art deep learning models, and typically many weight settings achieve low training loss, only some generalize. The implicit bias of gradient descent in SSMs with low-dimensional teachers provably leads to generalization in most cases. However, it can be disrupted by special training examples, so SSMs are susceptible to clean label poisoning. As for future work, we want to analyze the implicit biases of more complicated SSMs, for example, Mamba, to which we only use in experiments but not theoretically, and also to use our theoretical insights to derive practical defenses against this type of attacks on machine learning models. Thank you, and if you have any questions, I would love to answer them.
Thank you. Any questions? Yes, please.
That's a good question. They are not, I'm not aware of any works that explicitly find these types of images in existing data sets. However, there exist methods to create such examples, and the main point is that one can distribute such images and spread them in the web, and then when you train a vision model on I see. So in general, methods to defend against clean label poisoning are not so developed, mainly because it's very hard to detect which images would create such poisoning in advance, obviously. And that's one direction we want to pursue, to somehow develop a method to detect which data set and which data points could create problems before training a large model on them.
Any more questions? Okay, let's thank the speaker again. The next talk is from Bar-Ilan University. It's about Hyperpose. It will be given by Ron.
Hi, everybody. Thanks for having me. My name is Ron. I'm presenting the work of Hyperpose. It's hypernetwork infused camera pose localization and extended Cambridge dataset. This work was presented in CVPR and was conducted, under the supervision of Yossi Keller from the Bar-Ilan University. So first, let's define what the problem of camera pose localization is all about. So we're taking an image from a camera, handheld device, drone, car, whatever, and we're trying to estimate where this image was taken in the scene. The pose is generally described in XYZ coordinates and also orientation using quaternion. The leading method for this problem are feature matching, in which we extract features from the image and then try to find the correspondence in the 3D structure. SCR basically does the same, but regress directly the 2D to the 3D correspondence. We have relative pose regression, in which we take relative images from the data set, and then we try to match them for the query image, and then estimate the relative pose. And finally, we have absolute pose regression. This is the method we're going to focus in this talk, is basically trying to estimate the pose in a single step. If we compare the methods, we see that both the feature matching and the SCR methods are far more accurate, but they are slower because they need the matching, find the matching between the scene and extracted features. And the relative pose and the absolute pose are less accurate, but they are faster. And we don't need to know the structure of the 3D scene. So absolute pose regressions. So this is, in general speaking, this is the way this method works. So we take an image, we extract visual features from the image, and then we process that to find some meaningful task vector representation. This vector is being processed in the final stage to extract regress the pose, the orientation, and the pose. It's easy, it's very simple. And as you can see, it's fast, it's lightweight, and it's a standalone solution. You don't have to find a database or extract 3D scenes or other external knowledge. However, it's less accurate, and you have to train this model per scene. The first solution was presented by PoseNet, that's the genesis, and then following publication, we're trying to fix to enhance the accuracy by modifying the backbone, the loss function, the training flow, etc. Then came the era of multi-scene. We tried to tackle the problem that we just talked about, that you need to train a model per scene. And finally, the transformer era, in which we integrated attention-based solution. Why is it so challenging? Because we have dynamic and occlusion scenes. We have drastic changes in illumination, weather, differences in viewpoints and perspective views. Sometimes the scene itself doesn't have a lot of features, let's say a blank wall. And then, most importantly, the difference between the training and the test data. In this work, we propose Hyperpose, which is integrating the hypernetwork into existing or new absolute pose regressions models. And then the idea is to dynamically compute adaptive weights in real time, in inference time. So if you think about it, IPRs that were trained are fixed, and the only flexibility that they have is based on the inherited variance in the scene, in the training scene. Once it's given a new image, it has no way to actually adapt itself in real time. That's the incentive of integrating the hypernetwork. So here we can see the basic idea. You have on the left the basic APR, absolute poise regression, and then on the right we see integrating the hyperpose, adding and hypernetwork into the architecture. So that's the basic idea. For our experiments, we tested 3 different architectures. On the left, we can see the baseline APR we just talked about, and then we have the ATLOC, which is the leading scene, single scene solution, and MS Transformer, which is a multi-scene leading solution already published. Here you can see the difference between the original architecture and the enhanced one. The original architecture, the ATLOC, is being highlighted here in green, and the additional parts is the integration of the hypernetwork. Same goes for the MS Hyperpose, which is an extension of the MS Transformer solution. Again, the original architecture is highlighted in green, and the additional parts are the parts from the hypernetwork. Basically, you can see that the hypernetwork addition is added to the output of the original network, and then this is able to better accommodate for the changes in the query image, and we'll see that in a second. For the test, we have taken 3 different leading benchmarks in the domain, Cambridge Landmark and Oxford Robot Car, which are 2 outdoor examples, and the 7 scene, which is a leading benchmark for the indoor scenario. So here we can see the results on the Cambridge Landmark dataset. The table shows the average error in position and orientation in meters and degrees. And you can see that other than single results in the orientation on the Cambridge Landmark, on the in the King's College scene, the new enhanced hypernetwork solution outperforms the original architecture, both for the ATLOC and both for the baseline APR. Same goes for the indoor and outdoor additional data sets. We can see that not only that we are outperforming the original architecture, we're also introducing new state-of-the-art results in both single scenes, which are the upper part of the table, and the multi-scene benchmark, which are in the lower part. It goes both for indoor and outdoor. And last but not least, we have the Oxford Robocard. Sorry, this is a less common benchmark, but it is still an important one. And we can also see again that the hypernetwork variance is not only outperforming the original one, but also presenting a new benchmark in this dataset as well. And this is a very large dataset, which is showcasing this capability of coping with changes in illumination and occlusions and moving objects and so on. So if we focus on the Oxford robot car scenario, we can see that this graph showcases the relative translation error between the original Outlook architecture and the hyper network-based flavor. And you can see that as the color on the graph goes higher, brighter, so the error go higher. And if we focus on the left part of the loop, this is a single scenario in the Oxford dataset, we can see that the original model is having a hard time coping with differences in the illumination in this turn. So we can see that it goes from very bright to dark and then go back again to reasonable illumination, and the change in the translation is very high. However, when we have the hyperpose solution, it is able to cope better with that. Again, there is the degradation in the results, but it's far more reasonable than if you compare it to the original one. Same goes for the occlusion. Here we have 3 different images, following images from the Cambridge dataset, and we have the occlusion in the bus in the middle. We can see that in red, this is the original baseline APR that we talked about. It's having a hard time finding the pose when the bus occludes half of the scene. However, with the hyperpose, it's able to maintain a reasonable result. It's still below 1 meter,
Again, there is the degradation, but it's safe below the 1 meter benchmark, which is pretty good. We also see that the hypernetwork integration helps the scene transfer learning. And if we take lower number of images for training, still the enhanced model is able to train much faster and more accurate. And for example, with the translation on the left, we can see that even with 75%, it outperforms the original architecture. For better evaluating the robustness of the model, we have generated 3 different new flavors of the Cambridge landmarks dataset. That's the extended one, using generative models. So we can see it's the same scene, but only with a new flavor: the summer, the winter, and the evening. We took this new dataset and challenged the original models that were trained on the original Cambridge landmarks. This comparison was done without any retraining or fine-tuning. So the original models were trained on the Cambridge landmarks dataset, and this evaluation was done without any fine-tuning. And we can see 2 things. One, the enhanced hypernetwork model outperforms the original one. And moreover, we can see that the result that we get throughout the different variants are pretty much the same when we have the hypernetwork, unlike when we use the original architecture. So for example, if we take the the King's College row on the upper part, we see that it's modified from 0.89 to 1.15. However, with the hypernetwork, we are maintaining lower than 0.7, which is drastically different. So in summary, we are presenting the Hyperpose as enhancing any existing or new camera pose regression models by integrating hypernetworks. We have introduced new state-of-the-art results in both multi-scene and single scene, and we presented the extended Cambridge landmark dataset, which we hope will be adopted by the community to showcase the robustness of the new solutions. Thank you. Questions? Okay, I'll ask a question in the meanwhile. We know that hypernetworks are sometimes hard to train, depending on the architecture. Did you encounter any difficulties?
Sometimes, yes. We practice with a lot of different architecture and variances. It tends that less is more. So if you shift toward less complex hypernetwork architecture, it tends to be more stable and generate the best results. We started off with something more complex, and it did come up with a very, let's say, it had trouble to balancing between translation and orientation. It either really did well on the translation, but did really bad on the orientation, the other way around. But when we went for a more simpler architecture for the hypernetwork, then the magic happened. So we started seeing good results.
Any more questions? Okay, let's thank the speaker again.
Thank you.
While the next speaker sets up, let me just say that we have one less talk. The talk of 12:45 will be shifted to 12:30. Okay, so the next talk is from the Hebrew University, Dynamic Position Extrapolation for Ultra-High Resolution Diffusion.
Okay, thank you. Hello everyone, I'm Noam. I represent our recent paper, DIPE, Dynamic Position Extrapolation for Ultra-High Resolution Diffusion. It's a work done by Guy and myself under the supervision of Guy's supervisors, Yossi and Sagi, and my supervisors, Daniel Rana. Okay, so a bit of motivation on why we want to generate high-resolution images. So currently, the visual data we create and consume is of very high resolution, let's say 4K or 8K, but current generative models lag behind in this regard. So let's say imagine 4, a very giant model by Google, state of the art, generates images only on 2K. And let's say Flux, an open source state of the art model, which all the results will be generated using Flux, its effective resolution is 1K by 1K. So let's see an example of images, of 2 images using the same prompt, both using Flux. One in 1K by 1K resolution, and the other one using Flux and our type in 4K by 4K. That means 6 times the Flux resolution. So we can see the details and the very complex texture generated using our approach. So, okay, we saw why we want high resolution images. So let's dive a bit deeper to the results our model generates. Again, this is a model. This is an image generated using our model, using Flux, in 4K by 4K resolution. So also here we can see the very complex texture and fine details generated using the model. Okay, so a bit of background. So diffusion transformer, as I guess a lot of you already know, transformer is the state-of-the-art architectures at the moment. It seems for most tasks. And one cornerstone in its architecture is the attention mechanism. So this is how we perform attention in vision models or in diffusion models in particular. So we have the image or some latent, and we split it into patches, and then each patch is multiplied by some matrices WK and WQ. We get the Q and K vectors or matrices, and we multiply them, and this is the attention mechanism. Okay, that's good, but we are missing something here, because attention is permutation equivariant. So we need to add some positional information. So this is rope. This is currently the most widely used position encoding method. This is a figure from the original paper. We'll dive a bit deeper into it. So we have a sentence, enhanced transformer with rotary position embedding, and the positions of each token or word. So let's look on the first token. We have the word enhanced, and it's position 1. And then we split the feature to pairs of entries, and each pair is rotated using a rotation matrix, which its angle is m theta 1. M, it's the position, and theta 1, it's some constant. And as we can see, we have these constants for each pair. Those are different constants, and they are determined using a geometric series which determines by a theta base, which is a hyperparameter. Okay. So this is rope, and what we saw earlier can be visualized as a multiplication by a rotation matrix. This is the rotation matrix. We can see m and theta 1, and as we can see, we have this sine waves hiding in this rotation matrix. We will see them later on in the presentation. Okay, just to note, what we saw is for languages. For language, and in language we have the position is only an index, but for images, how we perform rope, we split the feature vectors into 2, and then the first half encodes the x position, and the second half encodes the y position. Okay, so now let's see an example and on what happens when we ask Flux to generate us images in high resolution, 4K by 4K. Those are the results we get, which are very, very bad. Specifically, we can see it's very blurry, and we can see some repetition. And let's see what happens when we generate the same images using with the same noise, the same prompts, and the same model using type. Those are the images we get. Okay, so as I mentioned earlier, we saw these sine waves, and now let's look a bit deeper into them. So what we see here, on the left-hand side, we see the training context. And on the right-hand side, we see the test context. That means we test our model on a larger context on what it was trained on. So we can see we have 2 frequencies here, a high frequency, the orange one, and a low frequency, the blue one. So for example, on the low frequency, we can take a look on these two positions. Those positions get the same value on the sine wave. That means that the model will think it is the same position. That causes the repetitions we saw earlier in the images. Okay, so the low frequencies are the one responsible for the repetitions. Okay, let's try to solve this. Some naive approach called position interpolation. That's just say, let's take all the position and normalize them to the training context. Okay, but then we get a different problem. We can see that in the high frequencies, or in all frequencies, we can see that the position come closer together, which causes loss of high frequency details, which results in blurry images. So the high frequencies are the one responsible for the high frequency details in the image. Okay, so a bit more advanced approach called NTK-aware interpolation says, okay, let's perform a different scaling to each of the frequencies. For the low frequency, we'll perform high scaling, strong scaling, and on the high frequencies, we'll perform weak scaling. Okay, this is good in intuition, but actually we saw that the highest frequencies are very, very delicate. We don't want to touch them at all, because if we touch them even a little bit, we will see blurry images. So then came Yarn, and then it says, okay, for the highest frequencies, we won't perform anything. This is PE. This is position extrapolation. We won't perform any scaling. On the lowest frequencies, we'll perform just position interpolation. On the mid frequencies, we'll perform some interpolation using scale factors interpolated between the PI factors and the PE factors. Okay, so let's now go to diffusion models. So we have, I guess most of you know, we have the diffusion models, take a data set of images, and we noise them using Gaussian noise, and we train a model to invert this process. Then, during inference, we can sample a Gaussian noise, and using our trained model to invert it into an image, hopefully that sits on the data manifold. So let's look at this process from the spectral domain. So here we have the PSD of the sampling trajectory, denoising trajectory. PSD is some metric on the magnitude of frequencies of images. So the black line, as we see, this is the PSD of Gaussian noise. And the red line is the PSD of a generated image. And the gray ones in between is the PSDs of the semi-noised samples during the denoising process. Okay, so let's look a bit deeper into this figure. So we have this part, which here, let's see, on the x-axis, 1 is a complete noise, and 0 is a clean image. And on the y-axis, 0 is low frequency, and 1 is high frequency. And the color encodes us for each frequency, we can see its difference from its value in this time step, then what it will end on the final image. We can see that low frequencies settles very early in the process, while high frequencies settles very, very late in the process. Okay, so now let's go into our approach, into DIPE. So our core idea is to take the static position extrapolation method, as we saw earlier, and couple them with the diffusion dynamics. So we introduce some scheduler, which takes as input t, which is the diffusion time step. And we have two hyperparameters, which we ablate in the paper. Intuitively, lambda s corresponds to the initial interpolation factor, and lambda t is the rate of change of the scaling factor. And we show two variants of our intuition. One is dynamic NTK-aware interpolation, which now we can see this kappa t we saw earlier. And we take the NTK-aware approach, and then we modify the scaling factor as a function of the diffusion time steps, which in the start of the process, where we have pure noise, we'll perform strong scaling, and near the end, we will not perform any scaling at all. Okay, So a second variant of our method is dynamic yarn, die-yarn, which also here we can see this kappa T appears. And the intuition is to take the scaling factors and modify them according to the diffusion time step, which in T equals 1, where we in pure noise will perform vanilla yarn, naive yarn. And then as we come closer into image, we won't perform any scaling. Okay, so a bit of results. This is some visualization of the method we saw. NTK aware and dynamic NTK aware are both kind of blurry, and NTK aware suffers from a lot of repetitions, while yarn and dynamic yarn are not blurry, but yarn suffers as well from repetitions. And just a bit of a teaser, DIPE also works for different backbones, for QN image, not only Flux. It also works for different tasks such as image editing and high-resolution video generation. And that's it. Thank you.
Questions?
Yeah, actually, we tried it. We have a comparison to a similar approach in our paper, and we can see that although in this approach the overall structure of the image is intact, but the high frequencies, we can see the texture, the fine texture, are not as good as in the in DIPE.
More questions?
Not specifically to multi-diffusion, but we did compare to some approach that works on Flux to generate images in low resolution and then upscale it in some way. Yeah.
More questions? Okay, let's thank the speaker again.
Thank you.
The next talk will be the last talk of this session. This talk is from the Technion and NVIDIA by Asaf Zingert and Noam Rothstein. It's called Time to Move, Training-Free Motion-Controlled Video Generation via Dual Clock Denoising.
Hi everyone, I'm Asaf Singer. Together with Noam, we're presenting Time to Move, a framework for adding precise motion control to video generation without any training. This is joint work with Amir Man, Ron Kimmel, and Or Litani. Modern video diffusion models like VO3, Sora, and LTX2 produce incredible realism, but they rely mostly on text prompts. Text is great for style and semantics, but too limited for spatial precision. If you're an animator, you don't want to describe a movement. You want to drag the object exactly where it needs to go. Prior work relies on training dedicated motion controllers to guide the video. While effective, this comes at a high cost. You have to fine-tune these modules for every single model architecture. These approaches also mainly target motion, while appearance is still largely controlled only through text. In contrast, we propose a completely training-free approach. It is efficient and plugs into any off-the-shelf model immediately. For inspiration, we turn to STEdit in the image domain. It's a powerful method that transforms crude user edits into realistic outputs. The intuition is simple. We take a rough input, add noise to destroy the artificial artifacts, and then denoise it to project it back onto the natural image manifold. Essentially, the noise acts as a bridge between distributions, connecting the user's core structure with the model's realistic texture. We adapt this logic directly to our motion control setting. We replace the crude image with the crude video, the layout with the motion cue, and project the output onto the natural video manifold. First, we generate a crude video as our motion signal. To create it, a user marks an object and simply drags it along a path. We used it to synthesize a warped reference video. As you can see, the motion is correct, but the video itself looks unnatural. The foreground is rigid, and the background is frozen and filled with interpolation artifacts. Now, naively applying SD-Edit has a few drawbacks. While SD-Edit preserves the coarse layout, the noising step then tends to erase fine details and texture. The structure is there, but the fidelity is gone. To solve this, we switch to a pre-trained image-to-video model. We condition the generation on the clean first frame. This anchors the identity and texture, while the noisy warped video provides the motion target over time. This preserves the structure and the appearance. However, we still run into a conflict with the global noise level T star. If T star is low, we preserve the user's motion, but the background freezes and warp artifacts remain visible. If T star is high, the background becomes realistic and dynamic, but the object drifts away from the user's path. A single global noise level simply cannot satisfy both needs. This leads to our following contribution: dual clock denoising. Instead of one global setting, we essentially run two different clocks at the same time. Inside the mask, we use low noise to strictly enforce the trajectory. Outside the mask, we use high noise to allow the model to hallucinate realistic background dynamics. This gives us the best of both worlds: high fidelity control for the object and realistic motion for the scene. The challenge is that standard diffusion models are designed to denoise the entire frame at a single global noise level. Naively mixing time steps pushes the input out of distribution, leading to artifacts. So how do we induce this dual clock effect? We start the standard denoising process at high noise T weak, but at every step, we override the object area by re-injecting our reference signal. We keep doing this loop until a lower noise level T strong. Once we hit that point, the object and background are synchronized. Then we simply release control and let the model denoise naturally.
So putting everything together, we get the following method. Given an input image and a motion instruction, we generate a motion signal. We add noise at the weak signal level, T weak, which corresponds to the higher noise level. Together with the initial input image, these conditions are image-to-video diffusion model. During sampling, we apply dual clock denoising. We take the motion signal and add noise to match the current time step, T-1. Using the motion mask, we inject this signal only within the object boundaries. Meanwhile, for regions outside the mask, we use the current denoised output, and these two components are blended together to create the input for the next denoising step. This denoising and re-injection process is repeated until we reach the lower noise level, T strong. From this point on, all regions are denoised until we get to time step 0. The result is a realistic video that preserves input details and accurately follows the motion control. Here we show some qualitative results of our method. Across diverse scenes, it achieves precise, realistic motion control while preserving the input appearance. A key advantage of our method is that it's completely plug and play. By operating strictly during sampling, it requires no training and works seamlessly across backbones, from smaller models like SVD to larger ones like One. As we saw, creating a motion signal from a cut and drag interface produces high-quality motion control videos. We show that it's also possible to generate a motion signal that creates camera motion. First, we predict the depth map of the image using a molecular depth predictor. Then we define a 3D camera trajectory. And finally, we use the depth and the trajectory to warp the image for each pose along the path, filling the holes with nearest neighbor interpolation and treating these areas as background values in the mask. From this warped video, we apply our method. The result accurately moves along the intended trajectory while ensuring that the motion and appearance remain realistic. Here is another example of a more dynamic scene. Since our conditioning is based on directly the crude video pixels, we can also control the appearance of the object in the warped video. For example, we can recolor it or modify its shape, or even insert a new object to the scene. Our method propagates these appearance changes into realistic videos while still respecting the original image content. We compare time to move, TTM, to the state-of-the-art method Go with the Flow. Crucially, Go with the Flow required thousands of GPU training hours, whereas TTM is training-free. Despite this gap, our method follows motion more faithfully while maintaining high visual quality. We also compare camera motion control. While Go with the Flow struggles with large motions and tends to drift, TTM produces smoother, more stable results. We evaluate our method quantitatively on both object and camera motion benchmarks. For object motion, MC bench metrics shows strong motion adherence and minimal unintended background co-motion, all while maintaining high video quality. This success extends to camera motion as well, where TTM also outperforms training-based alternatives. We ablate our dual clock denoising against vanilla SD edit and alternative schedules. The first two rows demonstrate the limitations of standard SD edit. Using a single high noise level results in a low motion adherence, evidenced by the high co-tracker distance. Conversely, a single noise level yields better adherence, but results in low dynamic scores. Dual clock denoising offers the best trade-off, where strong motion adherence in the mask region, realistic background dynamics, and high visual quality. So since releasing our model, it's been really exciting to see it's adopted not only by the research community, but also by real content creators, and even by desperate parents looking for a virtual way to handle kids jumping on furniture. Users have also discovered creative way to generate motion signals using real-life footage. For example, we've seen creators moving action figures with a stick to defined object trajectories, effectively turning a simple physical puppet show into a high-quality generated animation. Thank you for your attention, and please visit our website for more details.
Questions? So I have a question. The dual clock trick, this works without training, right? So do you think that you could get better results if you train the denoiser that is conditioned on the mask that says what variance you have in each pixel?
Yeah, I think the results would probably be better, but it's a disadvantage because then you need to train as opposed to the current methods.
Yeah. Any more questions? Okay, let's thank the speakers again. And this is the last talk of the session. We'll convene again at 1 o'clock.
Welcome back, everyone. Please try to make your way back to your seats so we can start on time. אציג אותך בפודיום כי הם עוד לא פתחו את המיקרופון. אז אני... כן.
Hey, okay. Okay, welcome back, everyone. We would like to begin the next session. So please quietly make your way back to your seat. Okay, I'm happy to introduce, we're starting off strong. I'm happy to introduce our first speaker, Vladimir Kulikov from Tomer Michaeli's lab at the Technion. And this paper, Flow Edit, hopefully many of you already know it because it won the Student Best Paper Award. So the stage is yours, Vladimir.
Thank you all. Is okay, the mic okay? Okay, I will begin. As you all know, text-to-image diffusion models have improved dramatically over the last few years, achieving high quality and excellent text adherence. Recently, flow models have also caught the community's attention. These models share strong similarities with diffusion, but proved to have better generation quality and sampling speed. Not just for images, also for videos. One task that people try to solve with these models is text-based editing. For example, given a source image with a text prompt describing it, say a photo of a cat, and a target prompt, a photo of a dog, can we obtain an image that adheres to the target text and remains loyal to the source image? Like so. The common approach to tackling this task with a pre-trained flow model relies on the concept called inversion. In this work, we present a method that breaks away from this common practice. This allows us to achieve state-of-the-art results. To understand our method, it is instructive to view editing as constructing a transportation from the distribution of images corresponding to the source prompt to the distribution of images corresponding to the target prompt. The backbone of our editing method is a generative flow model. So let's first understand how sampling with it works. Suppose we want to generate an image of a tiger, and let's say this is the distribution of tiger images. In flow models, we start by sampling a random noise image. We then gradually denoise it until we reach our target image. The process is driven by a velocity field, which points to a less noisy image at each time step. This velocity is predicted by a neural network,
which is conditioned on a text prompt, in this example, an image of a tiger. Now suppose we have a real image of a tiger, and let's say we want to edit it to become a cat. Namely, we want to transfer the image into the distribution of cat images. The dominant training-free approach is called editing by inversion. It starts by transferring the sample to the distribution of pure noise. This is the inversion process. This is done by conditioning the model on the source prompt, tiger in this example, and going in the opposite direction of the model's prediction towards a noisier sample. Now, from the extracted noise image, regular sampling is employed, with the target prompt cat in this example. This results in an edited image. However, it is well known that this approach creates a suboptimal coupling between the source and target distributions, and therefore many works propose to intervene in the process in various ways to improve the results. Here we propose an entirely different solution, which avoids inversion altogether. Before presenting our method, let us reinterpret editing by inversion. This reinterpretation is our first key contribution, and it serves the basis for our proposed approach. Specifically, we note that we can reuse the source and target velocities obtained at each time step by simply taking the difference between them to trace a new noise-free path. At earlier time steps of this path, the velocity is obtained from noisier versions of the source and target images, and therefore corresponds to coarser image structures. At later time steps, the velocity is computed based on cleaner images, and therefore captures finer structures. Importantly, by substituting the source and target velocities, we can obtain a standalone ODE that directly transforms source samples to the target distribution. Now, it's nice that we can traverse a noise-free path, but why is this good? This is basically just looking at inversion differently. So the target image is the same. However, this reinterpretation serves the basis for our method, which constructs a shorter direct path between the source and target distributions. Specifically, we propose to swap the inversion process with a stochastic one. We evaluate the source velocities on randomly noised source images. The average of these velocities effectively traces a different path. This change induces a different target path, driven by average target velocities. The difference between the averaged velocities is what creates our shorter direct path between the source and target distributions. This means that the edited image is more structurally similar to the source image while still adhering to the target prompt. To understand our method, let us focus on a simple two-dimensional example in which the source and target distributions are Gaussian mixtures with two modes each. In the context of images, this is analogous to editing car images into truck images, where both cars and trucks can be either blue or red. In this setting, we expect the editing method to map blue cars to blue trucks and red cars to red trucks. What happens when using editing by inversion? Let's look at several car images or samples from the source distribution. Here, blue points represent blue cars and red points represent red cars. In inversion, the source images are first mapped into the Gaussian noise distribution and then are regenerated with the target prompt to transfer them to the target distribution. Notice this approach leads to intermixed modes. In the context of images, this means that cars won't necessarily map to the same colored trucks. For example, this point here. In contrast, this is the path taken by our method, flow edit. As you can see, the modes are not mixed, which means cars are mapped to trucks of the same color. So why does editing by inversion impose this bad coupling? It is because the source points are deterministically mapped to the noise first. In this example, the diagonal green line splits the two source modes. Then, during sampling, the noise points are driven to the closest target modes, split by the pink vertical line. In this case, we can clearly see which points will be coupled suboptimally, marked by the shaded regions, like with the problematic point from earlier.
we propose a simple modification. Instead of using deterministic coupling between the source and target distributions, where a sample could land in a bad region, we use a stochastic coupling to obtain the noisy samples. Specifically, we are going to add random noise at each time step, starting from the noisiest. Now let's see how this solves the problem. So we start by adding random noise samples to the source point and calculating each one's velocity with respect to the source distribution, and average over the directions. Here, at the very first step, the average will be 0. And we do the same for the target velocities, which will also average to 0. We would want to drive our path using the differences between the velocities. In this example, the first step would leave us in place. But with each consecutive step, we are going to reduce the amount of added noise. Here, the source velocities will not cancel out, and the average will point to the nearest source mode. And the same for the average target velocity, which will point to the nearest target mode. And the difference between these average velocities is what drives our noise-free path, intuitively driving each source point to the closest target distribution. So we're going to repeat this process each time with less noise until we reach the target distribution. As you can see, flow edit achieves a much lower transport cost. While this is only an illustrative 2D example, we show empirically that for image distributions, we get similar qualitative behavior. Now let's see some results on real images using the Flux and Stable Diffusion 3 models. Our method can change big parts of an image without hurting structure, like the text in this billboard, from love to flow. We can edit specific objects, like changing this cat into a raccoon, and also changing this dog into a Dalmatian, while also removing the cat entirely from the image. Note that in all these examples, the edited images exhibit very high similarity to original images, while still adhering to the text. And recall, all this is done only by providing source and target text for editing, without any intervention in the neural network. Here are a few more examples. Here we change the steak into bread, preserving other details. And here we turn the lizard into a dragon with high fidelity to the original scene. And here the mountain into a volcano. Here we chain multiple edits, one after the other, and show the noise-free edit path. Even after 4 consecutive edits, the source background is still well preserved. We also compare our method to other competing methods on both Stable Diffusion 3 and Flux. As you can see with this example, only Flow Edit manages to both change the text on the gas station while preserving the other details, for example, the cars and the gas pump. We also conduct a quantitative evaluation using a dataset of over 200 image text pairs, both for Stable Diffusion 3 and Flux. We use CLIP to measure the edit's adherence to text and LPIPs for loyalty to the source image. So in these plots, we want to be at the bottom right. As you can see, in both cases, our method in blue strikes the best balance for structure-preserving editing. Our method is not only limited to images and can be easily implemented with text-to-video models. As an example, let's turn this car into a Hawaiian minivan, or this motorbike into a toy convertible car. Notice how the unedited parts are preserved. To summarize, we presented Flow Edit, which performs inversion-free editing, breaking away from the common approach, traverses a direct noise-free ODE path between the source and target distributions, and achieves state-of-the-art results on the task of image editing. Thank you for your attention, and you can check out our project page and meet us outside for coffee later. We will be happy to take questions.
Okay. Thank you very much, Vladimir. Are there any questions from the audience? Yes, here's a question.
Are you cycle consistent?
Who's asking? I'm just, yeah.
Are you cycle consistent? If you switch a cat to a dog, can you switch back to a cat again to the same result?
It's a good question. Actually, when we're performing anything, also with inversion, the case when we want to have a very, like, the target edit to adhere to the text, you're using imbalanced CFG schedule. So basically, for the source branch, you're going to use a lower CFG schedule, and for the target branch, a higher one. So only this alone already kind of breaks this cycle consistency. And we actually haven't tried doing this with balanced CFG to see if it works. But I would say probably not cycle consistent. Yeah, on the hunch.
More questions? Oh, there's one.
Yes, for the source branch we use, like, it depends on the model, but always the source CFG is a little less than the target CFG. It just gets a better trade-off in terms of text adherence. Yeah.
Okay, let's thank the speaker again. Is the next speaker set up? Okay, next we're going to hear from Rotem Gattegno. And Rotem is from Rachman University, and she's going to tell us about copy, transform, paste.
Okay, hi everyone. My name is Rotem Gattegno. I'm a master's student at the Canvas Lab from Rachman University, guided by, supervised by Oad Fried. And today we're going to talk about copy, transform, paste, zero-shot object-object alignment guided by vision, language, and geometry. Okay, so today it's very easy to find a lot of high-quality 3D meshes online. We can use many platforms such as Sketchfab to look for many meshes we want. For example, in here, we searched for Captain America. Separately, we can also look for the meshes of its shield. But those assets come unposed. We don't have any information about how they should interact with each other. So that arises the question, how do we automatically align those two meshes in a meaningful way? So we suggest copy, transform, paste. We start with the mesh of Captain America, and then we put on we add the mesh of its shield. We use the text prompt Captain America holding a shield, and our goal is to find an alignment where we have the final mesh that aligned with the text and also physically plausible. And here we can see a final output of our model as an example for what we want to achieve. Okay, but there is a lack of comprehensive data set. We don't have any data set that has the 3D object interaction, so that's why we introduced our method, which is a zero-shot optimization. So given the two meshes, let's say Pinocchio in its hat, and alongside the text prompt that describes the interaction, we are using copy, transform, paste to optimize the translation, rotation, and the scale of the hat relatively to Pinocchio until we get the final output, which is semantically correct and physically plausible. Okay, now I will show you how briefly the optimization is carried out. So we start by initiating the scene. And after initiating the scene, we take it and we pass it through a differentiable renderer. We use those views and we get the semantic loss. We will also use the geometric properties of the meshes to get physically plausible losses. We will use all of those losses, and we will optimize the final pose of the mesh. Now we will go into each one of those losses. So first of all, we wanted to guide the pose towards alignment with the textual prompt. So we defined a textual guidance. So as we said before, we start with two meshes. In here we have a candle holder and a candle. And we will pass it through a differentiable renderer with cameras we sample from many views. And we will pass it through clip image encoder. We will also take the input text, a candle inside the candle holder, and we will pass it through clip text encoder, sorry. We will get those two embeddings and we'll use them to get the semantic loss. So after, in here we can see an example. In here we have a coat rack and a fedora hat, along with the text prompt, fedora hat sits on top of a coat rack. And we use in here only the semantic loss. And we saw that
the Fedora head floats in space instead of being attached into the code track. So that's why we introduced another two geometrical objectives. The first one is the fractional soft ICP, where its intent is to align the source mesh into the target mesh. And the second one is the penetration loss, where its goal is to prevent interpenetration of the source mesh into the target mesh. Okay, so we'll first focus on the first geometric objective, the fractional soft ICP. I will explain it by using an example. So if we'll start with the candle holder and a candle that floats right above it, the natural idea is to use some well-known geometrical algorithm, such as soft ICP, to align them. Soft ICP is an algorithm that pulls the vertices of one mesh towards the closest point on the other mesh. But if we will do that, this is what we will get, because in here we will get the minimal distance between the vertices of the candle and the candle holder. And that's not what we want. We want only to take a fraction of the candle towards the candle holder. So that's why we introduced the fractional soft ICP. It's our variant we use in here, and in here we only take a fraction of the vertices of the candle towards the vertices of the candle holder. And we can see in here that our final alignment is as we want it, and only the tip of the candle touches the candle holder. So after we used it, we also applied it to the final optimization, and we saw that now the Fedora head touches the code track, but we still suffer from penetration. So we use the penetration loss. The penetration loss prevents invalid overlap by penalizing the intrusion of the source mesh into the target mesh. And now we can see that our final output is also aligned with the text and also physically plausible. After using this pipeline, we saw that often the optimization leads to premature convergence. So that's why we introduced the phased optimization. We wanted to start by exploring and then to move on to a local region. So I will visualize how it works. Okay, so in here we have an example of a rooster and a comb. And in the first phase, we can see that the comb explores the space around the rooster. In this part, the contact constraints are weaker, and we look for a smaller region that we want to later to be attached to. In each phase, we run each phase for a fixed number of steps, and then we take the best pose of each phase to initialize the next phase. We can see that in the second phase, we're looking in a smaller region around the rooster's head, and then we will take also this, the best pose from this phase to initialize the next one. We can see that in this final phase, the optimization refines the final alignment, and that in here, the physical constraints are stronger. So in overall, we use this phase optimization so we can balance early exploration with later contact enforcement. We also wanted to change what the model sees throughout the optimization process. So we wanted to do that by changing two things. First of all, we wanted to change the look at of the cameras we sample in the optimization process. So we interpolate from looking at the centroid of the target mesh at the first phase to looking at the centroid of the source mesh at the final phase. We also applied a gradually zoom in so we can throughout the process. So in overall, we ensure that in the first phases, the model sees the full capture, sees the entire, the two meshes, and in the final one, we are looking at a smaller region of the interaction area. And putting all of this together, now we can take a look at the results. Okay, so in here we have a representative example for one of the results. And here we have a golden necklace and also a stand, along with the text prompt, a stand with a golden necklace. And we can see that the method produces a semantically faithful and also physically plausible alignment. We also showed that we can use this formulation and we can extend it and we can use it iteratively. So in here we can see that instead of aligning just two meshes all at once,
we can do it progressively, and by that, to construct a full scene. And here we can see that we used it to construct the full burger in the iterative process. And here we can see several more examples across different pairs. And we also showed comparison to other methods. So when we started doing that, the language-guided object-to-object alignment was a relatively new problem. So we didn't have any other baseline that pursued the same goal as we did. So that's why we compared against two complementary classes of methods. We compared against two geometry-based methods and another two LLM-based methods that can pursue the same goal as ours. And here we can see qualitative comparison that illustrates the differences between those baselines. In here we have an example of an oyster with a pearl inside it. We can take a look and see that copy transform paste, which is our model, got the best result, which is the most semantically correct and also physically plausible. We showed also that this behavior is consistent across many other pairs and types. We also evaluated the method quantitatively. So we considered two complementary aspects of performance. So first of all, we wanted to measure the textual alignment, and we also wanted to measure the physical plausibility. And naturally, we saw that there is a trade-off among those two objectives. And we proved in our paper that our method got the best trade-off among those two objectives. We also conducted a user study, and we asked the users two questions about the outputs of all the baselines. We asked them which pose of which model has the best matches the description of the text. And we also asked which one is the most physical plausibility. And among both questions, our result got the highest score among all baselines. This trend, it also goes with the quantitative and qualitative results we saw earlier. Finally, we also wanted to show you that we can use the same formulation and we can extend it not to only text guidance. So in here we have, as input meshes, we have a wood and an axe. And we, as guidance, in here we have an image instead of text. So we wanted to guide those two meshes to be aligned as we can see in the image. And this is the final output we got. Okay, so to summarize, we today presented to you a zero-shot framework for object-to-object alignment, which is guided by vision, language, and geometry objectives. And in here you can see a lot of other results, and you can also check our GitHub page to see other more results and the optimization process and the benchmarks that we also published. Thank you.
Thank you, Autumn, for a very interesting talk. We have time for a couple of questions. Maybe, Sean, in the meantime, you can set up for the next talk. Oh, I see a hand over there. Yes, please.
If we have a really complex...
Maybe try to repeat the question so
maybe.
anyone...
Okay. I will repeat it?
Yeah.
It was really hard to repeat that one.
What I understood, tell me if I'm wrong, is that there are multiple plausible solutions and you want to know how the model chooses between those solutions.
Yeah,
in short.
So, okay, first of all, we do run the optimization multiple times, and we did it because we have multiple initializations, and we wanted to take the best outcome out of those processes. So we ran it multiple times, and then we will take the best among all of them using a metric that we have a fixed viewpoints and also the intersection loss. But if we have really complicated two meshes,
sometimes it will be really hard to find the right alignment. So we do struggle with weird and curvature structures, and we also showed it in our limitations that we also suffer from inserting something into cavity, because we saw that because it's one of CLIP's limitations, it gives a stronger value for when you have more pixels in the image. So if we hide some of the object, it will lower the score. So we do have those limitations, but we will try to tackle them maybe in the future. Yeah, so we're not starting with the scale, so because we're using LLM hyperparameter tuning at the beginning. So if we will ask, we give it a prompt, a candle inside a candle holder, and usually it will, in those cases, it will bring us, let's say, 1, and then we will change the scale of the source mesh to the targeted scale, and then we start from this point. So if you will have a large scale difference, we won't start by that, we will start from a different point.
Okay, in favor of time, let's thank the speaker again, move on to the next talk. Okay, the next talk, the next paper is going to be presented is called Silo, and it's about solving imaging inverse problems with latent operators. And the presenter is Sean Mann from the Technion, from Mickey Elad's group.
Okay. Hi, my name is Sean, and I'm a PhD student from the Technion. I would like to tell you about a recent work we presented in ICCV 2025 that utilized latent diffusion models at test time for image restoration. This work was led by Ron, who is also somewhere here, and advised by Mickey Elad. So, what problem are we trying to solve? There exists a clean image X, which we do not have access to. What we do have is a degraded version of it, Y, and Y was created by applying an operator A, an additive Gaussian noise N, and the operator could be linear or non-linear. In this example, we have A time by cubic downsampling. Now, our goal is to restore a plausible, sharp image that could have created our input Y. This is a real result from our method. Mathematically speaking, this means that we want to sample our restorations from the posterior P of X given Y. We are searching for natural images that are consistent with the measurements. Current solutions are based on diffusion models, which I'm sure you are all familiar with. Just for notation purposes, we will denote by X0 the image generated from the diffusion process, and by XT intermediate noisy samples. Diffusion model work by modeling the score function of our prior P of X. So it means that if we want to sample from the posterior, we need to model its score function. DPS is a fundamental work that uses Bayes' rule and Jensen inequality to approximate the posterior score from the likelihood and the prior. Please note two things. First, the prior score is presented here, meaning that we can use off-the-shelf pre-trained diffusion models. The second thing is that we need to define a likelihood function with regard to the current estimate of the clean image, denoted by X hat naught. DPS modeled the likelihood following the definition of the degradation operator. The resulting algorithm is extremely simple. We start from a random noise, and in each step from denoising, followed by a gradient step of our likelihood function. Now, DPS is a plug-and-play method, and such method has two main advantages. First, if we want to tackle a new restoration problem, we do not need to retrain the prior at all. This means that the prior acts as an engine that could power different restoration models when paired with different likelihood functions. The second advantage is if we have a new and better prior, we can just plug it in and improve our restorations. This is like replacing the engine under the hood and improving performance. So this brings me to latent diffusion models. Those models operate in a latent space of a trained VAE to produce a latent vector Z and are the current state-of-the-art models. Think about flux, image, and stable diffusion, and so on. A natural question is to how can we incorporate those prior into plug-and-play methods such as DPS? The natural answer to do so is that we want to sample from a new posterior, and we can do that with a similar derivation to DPS. The main difference is the likelihood function and its definition. We now need to decode our intermediate denoised latents at each step, and thus differentiate through the decoder. In practice, this leads to artifacts in the reconstructions. To address this, several follow-up papers proposed regularization to DPS in the latent space. For example, GML DPS adds a fixed point regularization, PSLD adds an orthogonal projection, resample several sub-optimization problems per step, and so on. But all of them have a similar structure. The gist is that we want to define a likelihood function in pixel space, so we need to jump between the latent and pixel space at each step. This diagram shows a single step. In practice, we need to repeat it hundreds of times. This is obviously problematic. First, it takes extremely long time at runtime, leading to methods that take between 5 and 30 minutes per image. Second, the gradient of the decoder are noisy because we apply to latents that are out of distribution relative to its training data. This results in artifacts, as we can see next. I have here a simple low-resolution image without noise. I'm going to show you the gradient of the likelihood function of the latent DPS with regard to the denoised latent at time step t. We can see that even in the early stages, there is a clear artifact in the gradient. This artifact will remain throughout the generation process and will show in our final restoration. A similar thing usually happens with more sophisticated methods, such as PSLD. And while the end result may be sharper than LDPS, it still contains artifact from the VAE. So this problem only becomes worse when we have noisy measurements. In this example, there is a small amount of noise, but the effect on some method is tremendous. This is resample. This is PSLD, and this is going to be our method. So before we proceed, I want to take a step back and understand the problem. The likelihood and prior operates in different spaces, and we need a way to combine them. And there are two distinct directions to go. The first is to decode the latents and compute the likelihood in pixel space. The second is to somehow encode the measurement into the latent space and compute a new likelihood directly in the latent space. While all previous methods took the first approach, we decided to work the other way. So in a top-level overview, prior method decode latents in each step and compute gradient in the pixel space. Silo encodes the measurements once and then compute the gradients directly in latent space. A few important questions come to mind. First, why can we just encode degraded images? What is the learned operator H? And how should we use it at inference? Let's try to unpack those questions. To test whether it is valid to encode degraded images, we compare the SDVAE reconstruction performance on natural images and their degraded counterparts. We see that the reconstruction performance on degraded images is higher than on natural images, validating our choice. Now, what do we want the operator H to do? If we assume it can mimic the encoded measurement, meaning it can degrade a clean latent, we show that we can define a new likelihood function which upper bounds the true likelihood function but operates entirely in the latent space. Thus, the optimization of the new likelihood function will improve consistency of the measurements while operating entirely in the latent space. The training is extremely simple. We just regress the encoded degraded images, and degrading images is an easy task. So, meaning that we can use extremely small networks and train them very quickly. How do you use this trained operator at inference time? This is the entire silo inference algorithm, and this is practically DPS, but with our spatial operator. We start from random noise. We encode our degraded measurement once, and in each step perform denoising, followed by a gradient step of our newly defined likelihood function. No need to decode anything. In the end, we decode the restored latents as our final result. And the result, in short, are better perceptual performance with significantly faster runtimes. And even when we consider the training time of our latent operator, average over 1,000 test images, we achieve a speed up compared to prior methods. We tested Silo, and it is sought across degradation, priors, and perceptual metrics. And now I would like to quickly cycle between a few examples. Here we have an in-painting problem. This is the naive application of DPS in the latent space, and this is Silo restoration. This is the Fox from before. This is PSD restoration, and this is our restoration. Here is a noisier image, a prior method, and Silo restoration. And finally, again, an in-painting, resample, and Silo. Now, as Silo attempts to sample from the posterior, we should be able to explore it, and we can do so by changing the seed between generations. All valid solution to the same degraded input. There is no cherry picking, just incrementing the seed. And with this, I want to conclude. And in summary, latent diffusion models are great priors for plug-and-play methods, but the VE is unreliable and introduces artifacts. We can bypass the VE by training a simple latent operator, leading to better results in less time. Thank you very much.
Thank you for the very interesting talk. There's time for a few questions. Oh, there's one. Yes, please.
Okay, so yes, we tested.
Maybe repeat the question.
The question was, we tested it on natural images. Does it work on text and other modalities? Actually, we tested it only on natural images because ImageNet is currently de facto benchmark for this kind of tasks. But as long as your prior should be able to generate text, you should be okay. We did not test it specifically. We expect that other modalities like, I don't know, medical imaging might be more problematic because the encoder is totally different, but you can probably train an operator for this specific case.
More questions? I have one quick question. So as you were training already the operator to work in latent space, there's one other inaccuracy that all plug-and-play models assume, which is the X0 hat is the one being evaluated, right?
Yeah, so there is a hidden assumption in DPS that we use the approximated denoised image instead of the real denoised image. We also make the same assumption, so we work in the same regime of all the other methods, but as we do train an operator, we could leave this assumption. We did not write in this paper because we wanted to be as fair as possible.
Okay. Okay, let's thank the speaker again. And I'm happy to introduce our next speaker, Doron Cerebro. Okay, Doron, please set up. And Doron is from Ben-Gurion University, and he'll tell us about HIDA, or HIDA, I guess, because it's hypernetwork for test time domain adaptation in medical imaging.
Hello, everyone. My name is Doron Cerebro, and I'm going to present my work, HIDA, Hypernetworks for Test Time Domain Adaptation in Medical Imaging Analysis. This work was done under the supervision of Professor Tami Riklin-Raviv and published in the latest MICAI. So let's start with some motivation. Consider the following common scenario. You have some well-curated data set, you train your neural network on some task, and you obtain accurate predictions. But as you use real-world data and you use the same pre-trained model, performance degrades. This is likely due to a domain shift, a difference in distribution between the curated dataset and real-world datasets. In the medical domain, this is a real challenge, as domain shift can come from a myriad of reasons. It's different in acquisition protocol, different imaging hardware, such as MRI scanners or some other machines, difference in populations, and many, many more. To overcome this, we use domain adaptation methods. A common approach to domain adaptation is domain invariant learning, in which models are adapted
to abstract away the domain signal and learn domain agnostic features. These can then be used for downstream tasks as if no domain gap ever existed. This works and is widely applicable, but it has two limitations. First, it treats the domain information as noise rather than signal, leaving valuable information unattended. Second, it in many cases requires access to samples from the target domain, though unlabeled, during training, which is a practical limitation for clinical applications. Another set of approaches, test time adaptation, adapts model on the fly by imposing some statistical prior. For example, tent is a method that takes class probabilities of classifiers and use on-the-fly short optimization loops for batch normalization layers to enforce lower entropy and thus creating a confident prediction. While this works, it still ignores the domain signal and is very task-specific. In this case, it's limited to classification models. So in this work, we aim to bridge the gap between these two methods by being both domain-aware and adapting on the fly. To phrase this differently, our main question is, can we leverage domain characteristics rather than suppress them? And if so, how do we condition models to become domain-aware? So let's start by the conditioning part. If, for a regular network, the parameters of the model are governed solely as a function of the input data X, which is trained and backpropagated, we want to condition a model by some external factor, a conditioning input, and we use a hypernetwork to do that, which is simply a hypernetwork that takes some external input and maps it to parameters for our primary network. So in this case, our conditioning factor is the domain. So for one set of domain characteristics, we get one set of weights, and for a different domain, we get a different set of weights. So this will be our conditioning mechanism. Now, what about domain representation? How can we represent domain in a way that will be useful for the model and tailor the predictions to become better than just ignoring domain characteristics? So for this, in the scope of our work, we limit ourselves to two assumptions that are not too strict. First of all, the domains we're talking about are within a single modality, meaning we're talking about difference between different CT scanners or the same scanner in different hospitals, not CT versus MRI, per se. And secondly, we're talking about a covariate shift and not a label shift. All that means in simple terms is that what defines the domain is strictly a function of the medical image itself and not the label, meaning that I can encode the image directly to get some domain signal out of it without needing any labels. And when I talk about a good representation, what I want to obtain is something that is on one hand well clustered, but more importantly, it preserves some cross-domain relationships such that if I project new samples into the domain space, they will be well represented as some interpolation of previously known domains. So let's take a practical example. And the way I'm going to solve this is by training a domain classifier, which is something that is very easy, because what defines domain in this case is the hospitals from which the medical scan came from. And for practical example, let's say I have 3 domains, and I train on only 2 of them because they are available to me. And that is a very easy task. But I have a third domain that I have not seen. So then I can project the learned representation to some 2D visualization, in this case t-SNE, and I get the following plot. Now, as expected, the orange and blue domains that were available during training are well separated, and every sample represents a different scan in this space. And you can see that the samples from the green domain aren't randomly scattered across the space, and they're not clustered somewhere far off to the side. They're meaningfully represented within the domain space, spanned by the blue and the orange domain, meaning that I get some sort of relationship between the green samples, the green scans, and the ones that I know. This is exactly the type of conditioning I want to pass to a downstream model to perform better on tasks. These can be regression, classification, segmentation, you name it. So now that we have all of our puzzle pieces in place, let's build HIDE. So we start with our primary network. And again, this is a general purpose method, so this can be any network, segmentation, classification, you name it. We schematically split it into an encoder and a prediction head, but this can be done for virtually any network. The head can be a decoder, it really doesn't matter. And to that, we add the domain classifier from the previous slide. And to connect it all together to perform the conditioning, we add a hypernetwork that takes the learned domain representation and conditions it on the primary network to present domain-aware signals and thus tailor the prediction of the model to the domain characteristics of the input samples. Let's dive slightly deeper and look at the implementation of the hypernetwork. So in order to perform domain conditioning, we are not limited by any specific architecture, except some practical limitations for hypernetworks that are beyond the scope of this talk. For our work, we took the simplest possible implementation just to show that this is possible. By that I mean that there's only a two-layer MLP. The first is an input projection layer, and the second is an output layer to map to whatever layer in the primary network I'm generating weights for. This can be a convolution kernel or a linear layer, just in this example. And we also output the projection as auxiliary input. We use that for training. So let's talk about training just a little bit. So our model is trained end-to-end, governed by two losses. The task loss, which is comprised of the loss of the primary network, which is, as it would be, cross entropy for classification, focal loss, or whatever the primary task the network is trained on, it's trained on as it would. And it is regulated by two terms. One for back-propagated weights. Those are the weights that are learned via back-propagation. And a second regularization term on the output of the hypernetwork, which are the generated weights. This regularization ensures a stable convergence towards the two different kinds of weights in the primary network. The second loss is the domain loss that is trained using cross entropy, as you'd expect, but also multi-similarity loss, which is a generalized form of contrastive loss from the world of metric learning. And this is what ensures that our latent space for domains is not just well clustered, but also well represented, and especially creates the meaningful relations between the domains that I previously showed. Note that in this system, the only component that receives supervision both from the task and the domain losses is the hypernetwork, thus allowing it to be the bridge between the domain gap, between the domain branch and the primary network. To showcase how general purpose and effective HIDA is under different settings, we conduct two experiments. And these differ in task, in modality, and in the number of available domains. So the first experiment is for chest X-ray classification in 2D, with only 2 domains available during training, meaning this is the minimal number of domains to span a domain space. And the second experiment, brain age regression on 3D MRI scans with 20+ domains available during training. Evaluation is done in a leave one out manner, meaning that we train on all available domains except one and evaluate on the unseen domain to simulate adaptation. So, for the chest X-ray pathology experiment, we take 3 well-studied datasets that share 5 pathologies that can all co-occur within the same scan, making this a multi-label classification problem. For the training, we rely on a previously established benchmark called ChecksNet, which uses a backbone of DenseNet 121 for the primary network. And our domain classifier is a small CNN, and the hypernetwork is a small MLP, all orders of magnitude less parameters than the primary network. And the hypernetwork generates weights for only the final output layer of DenseNet. So before we dive into results, let's look at the domain embeddings. So for reference, this is what we get when we train on all 3 domains, the domain classifier. And as you'd expect, all 3 domains are well clustered because this is not a hard task. What's interesting to see is how these relationships are preserved when I leave one out, but still project all 3 into the same domain space. So there's a lot to unpack here, but let's focus on the small cluster on the side for the blue domain, NIH. And even when I leave that out and it is unseen during training, that is still preserved, meaning our latent space for domain representation is still meaningful, even when it's only spanned by 2 domains. And this is also evident in our results, where we compare ourselves to a supervised baseline and to domain invariant learning method and test adaptation methods, and we outperform all of them. And for the second experiment, where we use brain MRIs to predict a continuous age, we use roughly 30,000 brain MRI scans from 20 different domains, meaning the variability is much higher. We can still show that, as you can see here in this t-SNE plot, that there are clusters that make sense. Some of them overlap, some of them are more well-defined, but the more important thing to note is that there are meaningful relationships in this plot. And as you can see, when I project a new domain that was not seen during training, it is still meaningfully represented within this plot. And this is also evident in our results, where in this case, an interesting phenomenon is that not only that we improve over the baseline in a leave one out setting, we also improve over the baseline in a fully supervised manner when there is no adaptation at all, which leads us to hypothesize that this improvement means that being domain aware is useful under any setting. So to summarize, we showcase HYDE as a general purpose framework that fits under any task, modality, or model architecture to perform on-the-fly adaptation using the power of domain interpolation. We thank you for your time.
Thank you for the very interesting talk. Any questions? We have time for a few, because you guys were all very disciplined and finished on time. Any questions here? Yes, there's one over there. We can't hear you from here.
Yes, in the interest of time, I kind of limited. Multi-similarity loss is a work from CVPR 2019. It's just a mathematical framework to generalize over a bunch of metric learning losses and kind of sort of a weighted sum of all of them, which includes both triplet loss, contrastive loss, and a few others, I think, under the same mathematical formula. In a nutshell, it allows you to pull together similar examples and pull away dissimilar examples, but not only looking at individual examples, but over the entire batch, which is what allows you over cumulative batches to get a really, let's say, a nicely behaved embedding space. Can you repeat that? So I do it across domains. I optimize the domain classifier on it, and I optimize the inner representation of the hypernetwork such that the learned representation space is nicely behaved with respect to different domains. This is what allows us to create those nice t-SNE plots that you saw earlier.
Another question here.
So this could be trained end-to-end, starting completely from scratch. But we did experiment with starting from pre-trained, both for the primary network and for the domain classifier. We found that it doesn't affect performance too much. There are trade-offs here and there. It mostly reduces the training time required until convergence. Usually the domain classifier converges really fast because it's a relatively easy task. Even across multiple domains that we tested this. The primary network, that really depends on the tasks that you're doing. Obviously, we were limited with the amount of experience we could have done, but I'm guessing it's more the training dynamics of the primary network rather than the entire dynamic of the system.
Okay, I'll ask one more quick question. So something that was very interesting to me, and correct me if I didn't get it correctly, was that the domain classifier seems to generalize better than your main network. And this seems to be like one of the biggest takeaways here, right? That it's better to kind of train a simpler task like classification that you can extract generalizable representation to use later on. I'm wondering if this is something that you witnessed in this specific data set. Is it like a general claim or statement? If there's some more support to this term, to this claim to make it more general?
Yeah. So that's a good observation. We tried in earlier experiments to do some more, let's say, directly derived injection of this representation via cross-attention or something more common, let's say. And we saw that it is, once you make it part of the primary network's architecture, it's a lot harder to converge reliably. And by externalizing this task, we can ensure a more reliable convergence and being better than the primary network, simply because I believe you are correct in stating that training the domain classifier in and of its own is an easier task. Even if you simply have to inject it via hypernetwork, which is kind of rough to train, it still is more reliable than trying to do this all at once with the primary network.
Okay, let's thank the speaker again.
Okay, so there was a last-minute change. Miriam, which was supposed to give the next talk, couldn't make it. So if you thought you're going to give a talk in 15 minutes, surprise, it's right now. Meir, I think? So you're up. Sorry for the last-minute thing. So I would like to introduce Meir, that will tell us about, let me cheat,
Clip latent space.
clip latent space.
Oy. Okay. So, hi, everyone. I'm Yossi Levy, and I'm a PhD student under the supervision of Professor Guy Gilboa from the Technion, and today I'm going to talk about the latent space of clip. So, before I dive into our insights, let's shortly explain what clip is and what is already known on its latent space. So clip is a joint text image embedding trained to embed positive pairs close to each other in terms of cosine similarity, while push the negative pairs farther apart. It is a pioneering work that invokes a wide range of tasks, including classification, retrieval, segmentation, detection, synthesis of images, editing, and many more. So if I will ask you to image how the latent space of clip is look like, I guess that many of you would imagine it as something like this, where an image and the corresponding caption are embedded close to each other, like in this cat image, or this dog image, or this one. But the truth is actually different. The image and text distributions are separated. You cannot find image sample inside the text distribution, and vice versa, a phenomenon called the modality gap. Another, maybe less known phenomena is the narrow cone effect, where each of the distributions lies within a very limited angular scope. So now I'll dive into our insights of the paper, The Double Ellipsoid Geometry of Clip, which we presented in ICML 25. So if this is the structure I described earlier, then we analyzed the unnormalized features on MS-COCO dataset and found that clip is actually of a double ellipsoid structure, where each of the modalities span its own ellipsoid. Now, let's analyze the properties of the space. Here, we revalidate the modality gap phenomenon, but we show that you only need 2 tag features in order to separate the space perfectly, and you don't even need the entire feature vector. This is again on the MS-COCO dataset. This is not a PCA or a UMAP of the space, it's just 2 tag features. Okay. Another property is the thin shell property. We analyze the centralized features, and we see that the norm of the features must reside within a very narrow region. Namely, that features could not reside anywhere on space, but they are limited into a very specific region in the thin shell. Last property is the anisotropy of the space. We analyzed the covariance matrix and found that there are entries with much higher variance than others, suggesting that the space is anisotropic. So now, when we understand better the geometry of clip, we can analyze how clip reside common and rare samples. We start with a naive approach to measure how common the sample is. We compute a cosine similarity from this sample to all other samples in the set and average it. This is a conceptual measure estimated how common the sample is. We termed it as conformity. The second measurement, the estimated conformity, is a geometrical measurement, and it goes like this. First, average all samples in the set and get the modality mean. Now, Now compute only a single cosine similarity from this sample to the modality mean. So this is the estimated conformity. We found a striking linear correlation between the conformity and the estimated conformity. And the estimated conformity suggesting that samples are conformity suggesting that rare samples reside far from the modality mean, while common ones are aligned with it. To get some impression, here are several images with high and low conformity. The images with high conformity tends to be of a very general scenes, while the low conformity images tends to be of a very distinguishable faces, or when text is embedded inside the image, like in the Scott Brown example in the left bottom image. Now I'll move on to the second paper named White and Clip as a likelihood surrogate of images and captions, also presented in ICML 25. This is a joint work together with PhD student Roy Betzer
and obviously Guy. So we already saw that the latent space of a single modality looks like this. Now we suggest to first centralize it and then to apply whitening transformation, namely to diagonalize the covariance matrix. So if we start with an anisotropic space, then after whitening, we end up with isotropic space. So for this W-clip space, we found that it is actually Gaussian. We measure Gaussianity through two Gaussianity tests, Anderson, Darling, and D'Agostino-Pearson, and observe that most of the features are roughly Gaussian. So for a standard Gaussian distribution, we can explicitly write down its log likelihood and see that the log likelihood is negatively proportional to the squared norm of the features. Thus, as the norm goes higher, the likelihood gets lower. So the pipeline is, given a population of samples, we use them to compute the whitening matrix. Then, given a new sample, we can whiten it and compute its norm. This process is simple and fast, and the whitening transform is invertible, so you can plug it into any pipeline where clip is embedded in. Here we show how we use the log likelihood to identify images with artifacts. We used real images as population, and we saw that artifacted images have lower log likelihood. And here, we analyze the likelihood on an out-of-distribution datasets. As can be seen here, when we applied it on ImageNet C, we observed that as the corruption is more and more severe, the norm of the whitened sample is higher, indicating a lower log likelihood. So to sum everything up, I introduced the structure of CLIP and showed that it is of a double ellipsoid structure. I showed the conformity measurement, where common samples reside close to the modality mean, while rare ones are far away from it. And I showed the log likelihood, where on the whitened clip, the norm is correlative to the log likelihood. Thanks for listening.
Thank you. Any questions? Questions? I have one. So you really investigated the latent space, but you were given the model, you were given CLIP, right?
Yeah.
Now that you know so much about the latent space, let's say you had enough resources to retrain CLIP. Do you think of ways to kind of like improve the latent space? What would make it better?
So one of the things that you might think of is to apply the whitening transformation somehow inside the training phase, and then you will end up with something more nice to work with. So this could be one direction, but I guess that it could be many more.
Okay. Thank you. Other questions? Okay. Let's thank the speaker again. Cool. I would like to introduce Nimrod now, which will tell us about our favorite platform, Archive, and what you can do with it.
Okay, hi everyone. My name is Nimrod. I'm a PhD student here at Tel Aviv University under the supervision of Professor Raja Jiris. And today I'll talk to you about LiveKive, which is our multimodal benchmark. So I guess you're all familiar with it once a new model comes out and it's got like really astonishing results and it crushes all the benchmarks and reaches superhuman capabilities. But once you take it into a real-world spin to your problem domain, it's usually perform much worse. And there are probably many factors to that, but today we're going to focus on one, which is test set contamination. Basically, in vision language models, they basically train on everything, whatever they can put their hands on. And in some cases, they might even train on test set, which is exactly the test set contamination.
And this can lead into falsely superhuman performance and even get static benchmarks to get saturated and actually false impression. So basically our research question here is to what extent this test set contamination actually affect those performance of models. So to tackle that, we introduced LiveKive, which is basically a live benchmark using on archive papers, which continue evolving, meaning we can publish a new test set every time period, and that in this arm race of model versus benchmarks, we can always have one version that the models did not see. We also use our benchmark to be fully automatic with no human in the loop, which makes us, we can actually enables us to make it at scale and actually produce a new version whenever we want. And this reducing of test set contamination risk enables us to have much more accurate measurements. So below you can see like a general flow. Once we decide to have this version, we take the archive papers, we build our data set, we evaluate it over many models, and we need to do it efficiently, so I'll talk about this later, and then we can have our evolving leaderboard. So I'll start with basically how we did it. So the first part is basically to take and harvest archive, and we do structure processing from it for all the figures and tables, and they're captioned, and this is like our raw data. Then we pass this whole data into what we call a capable VLM. Back in the day, it was GPT-4o, which basically gets this, the images and the captions, and it can generate us multiple choice questions with the ground truth and also negative options. But we know that models can make mistakes and can hallucinate, so we also propose a multi-stage filtering in order to deal with that. So the first part is actually passing all the questions in LLM and reduce and filter out all the questions that actually an LLM can answer without the image. So for example, if I ask you what color is the sun, you probably don't need an image for that, and this image is not really relevant. So this keeps our benchmark truly multimodal. The next phase is basically take another VLM and give it the triplet of image, question, and answer, and ask it, is this triplet valid? Meaning the question relates to the answer, and the the question relates to the image, and the answer is correct to the question. And this phase also turns out to be highly effective and reduce hallucinations. So here you can see some results. We have on the left side results of a table with a multiple choice, and you can see that basically we have some arithmetic here and not just extraction, which is wasn't that common when we worked on it. It was even before reasoning models, so it took a little bit more effort. And on the right side, you can see some example for chart understanding as well. Okay, so now once we have this data set, I didn't talk about the numbers that much, but we get into around 15,000 samples at each version, which is highly large. It's rather large static benchmark, so we need to evaluate it efficiently, especially if you want to evaluate it over lots of models. So basically, in order to make it less computational expensive, we propose a statistical approach, which was based on previous works. The main approach of this method is basically to assign to each model a skill level, which is how well it managed to answer questions, and for each question a difficulty level, which is how many models manage to answer that question. And then what we do basically is we take the first version and evaluate all the model on it, and then we can assign the model skills and the question difficulties to all the models and questions. And then when a new version comes out, we can choose according to some budget, subset of models, could be 3, 5, 8, whatever we choose, and basically evaluate only those models on the new version and assign new difficulties to the questions. And then when we have the new difficulties and the model skills from the first version, we can actually predict how well the model that we did not evaluate will perform.
And this turns out to be quite accurate and also reduce the computational burden by around 17 to 85%, depends on the budget and the number of models we have. So maybe just to sum up in numbers, so we basically reduced a new version every month. We have it over 350 papers from 14 different domains, from CS, AI to physics, biology, and so on, and we produce around 15K questions for tables and figures. So here's like a big table from our first version, but if we kind of zoom in, what we can see is basically that really the proprietary model and Claude Sonnet back in the day was really dominate, and open source models such as Qwen and InternVL were pretty good back then. As we know, they are good now. But since I already mentioned that these models used during the training, during the creation of this data set, you might say that, okay, maybe the evaluation is skewed, but we did lots of ablations and games in the paper where we switched roles and did several subsets from versions and leave one out and did all those ablations in order, and in all those cases, the ranking of the models remained the same, meaning it did not contribute or misharm the link board. The bottom table, which I want to focus, is basically our human evaluation. Since everything is automatic, we actually verified a subset, which is over 1,000 examples, and we evaluated the models on it and on the full version, and you can see the deviation is rather bounded. We did that for several versions as well. I'm only presenting the first version here. Okay, so up until now, I told you about the data set and the motivation, but I never closed the loop about contamination. So we tried to show some hint here. What we did is basically, since we're dealing with archive and documents understanding, we took some well-known static benchmarks that dealing with documents understanding. And since everyone has a different metric, we took the relative ranking of the models on those benchmarks, as of course lower is better. And once we have this relative ranking, we took the same approach and compute the relative ranking on our live Kai version. And what you see here is highlighted is basically models that perform very well on the static benchmarks, but perform much worse on our benchmark, which might hint contamination. Regardless the effectiveness of our efficient evaluation on time, we show here 3 additional versions. And what we did is basically we did a full evaluation on all those versions and applied the efficient evaluation method. And we compute, from the left, you can see the correlation between the ranking, between the predictions of the efficient evaluation and the full evaluation. And on the right side, you can see the mean absolute error of the total accuracy. So you can see it's rather robust. So to conclude, we propose LiveCav, which is a live multimodal benchmark at scale, which we can update continuously. And in order to make this live benchmark evaluation feasible, we equipped it with efficient evaluation framework that reduced the computational burden a lot. We published our data set, the code for the generation of the data set, efficient evaluation, and of course the paper. Thank you for your attention.
Thank you. Questions? Questions. I have a question. So if I understood correctly, your pipeline is automatic, right? Use the LLM, the VLM, etc. Do you try to validate using maybe sampling and human evaluator or something just to make sure you're not kind of like fooled by the automation?
Yeah, so I've talked about it. For each version, we took over 1,000 examples that I manually verified, and we test the models and
how will it work for the live? So you said it can be like a live benchmark with new version. So you plan on continuing to do that for each new version?
So in the paper, yeah, I did that for like 3 or 4 versions in order to validate the method, but yeah, basically.
Thank you. Other questions? Okay, so we are ahead of schedule, which is extremely rare. Let's thank the speaker again.
let's try to keep ahead of schedule. So unlike what's written in the original schedule, let's reconvene at 3:45. Thank you.
Okay. Slowly but surely take your places, please. We are ready to start the last session of the day. Thank you for sticking around. And we'll start in a minute. Okay, we can start. So the first talk of this session will be given by Gur Elkin from Ben Gurion University on my favorite topic in the world, solving jigsaw puzzles. Go ahead.
Thank you, Shai. So today I'm going to present my thesis work about reconstructing jigsaw puzzles using sequence-to-sequence models. So basically what we're doing is we take this classic computer vision problem and we cast it into the language modeling domain and are able to isolate the non-visual features of the problem and utilize them for completing our mission. So basically, this is trying to solve a vision problem using non-visual models. So we'll be focusing on jigsaw puzzles. They have several applications in the real world. Everybody knows and have fun solving toy puzzles. But of course, we also have critical applications such as archaeological reconstruction, something dear to our heart in the lab. Some papers talk about implementations in document reconstruction, image editing, processing of genetic information, and many, many more. So the most fundamental variant of the problem, there are many, many variants, but the most fundamental one is square jigsaw puzzles, where the images, in fact, the pieces are given as square images, and we want to find a mapping, some function to map each image to an index on a grid coordinates system. So these images could be noisy, could be eroded in so many ways, and could also be missing each kind of challenge, making the problem more hard to solve. So we looked at the current paradigm, and because we are talking about images, the vast majority of works go in the following direction. We will extract visual features from the pieces and try to use these visual features to guide the reconstruction of the puzzle. However, there are other features, we call them semantic features or high-level features, which are not inherent to the pieces themselves. We can think about an example that want to solve a puzzle of a face. We as humans know that the eyes should be at the top of the puzzles, the nose in the middle, and the mouth at the bottom part, but we cannot infer this structure directly from the images. So we wanted to isolate these features, these high-level semantic features, and try to solve the puzzles just using these features. So our research question was, can we reframe the problem of puzzle reassembly as non-visual, symbolic, tokenized, sequence-to-sequence modeling problem? And can we solve puzzle using this formulation? So what we basically did was building a two-component system. The first component, our tokenizer, takes pieces and describe them as discrete tokens, short discrete token sequence. These discrete representations are fed to the sequence-to-sequence model we see in the middle, generic BART, T5, LSTM, generic sequence-to-sequence model, which should output the correct arrangement of the pieces by indices. And in fact, as you can see, in the green rectangle,
This is a classic NLP or sequence-to-sequence language problem with no visual features. So why am I saying there are no visual features here? In fact, our tokenizer takes the images and infers some discrete representations, I call tokens, from these images. But when the model receives these tokens, it has no idea of what drives this part of the image to be called 11 or 14. It only sees the symbol and has to internally represent in its embedding module what this symbol means without relying or having direct access to the images themselves. Okay, so how is the tokenization process done? We begin by taking all the training pieces and view them as a bag of pieces, and we want to train our tokenizer in the following way. We divide each piece into T by T patches. T is a hyperparameter, we'll ablate later. We take these patches, each one would be corresponding to one token, vectorize them, and using PCA, project them to a lower dimensional space. In this lower dimensional space, with the lower variant between patches, we conduct k-mean clustering, and later at inference, we identify each patch with the index of its closest centroid. After we obtain these centroids, we can associate each patch with a relevant token. And to make all the thing a bit more efficient, we only regard the frame or the border of the piece. We extract this token laying on the border of the piece in clockwise order, actually reducing the memory complexity from square to linear in T. Okay, so this short sequence should represent one piece in the puzzle. All the puzzle pieces undergo this procedure and then concatenated to create one long sequence that represents an unsolved puzzle. So this is the input to our tokens, how we evaluate its outputs. We have actually two metrics, well-established metrics for measuring the quality of reconstruction. One is called absolute accuracy, which measures how many pieces have we placed in the right place. So in the example, we have 77% or 7/9 of true reconstruction, reconstructed or not. So it's either 1 or 0. We measure our model on 3 well-established benchmarks. One is called ImageNet 3x3, which is actually just images from ImageNet divided into 3x3 parts. Later, we also measured on JPLeg, which is a dataset that tries to follow or takes inspiration from the archaeological scenario I've discussed before. It contains images of artifacts and artworks from the Met dataset, and then it divides it also into 3x3 or 5x5 puzzles and takes a random crop within each of these pieces to create some kind of an erosion, making the reconstruction much harder. So before I present the results, I want to emphasize our model have this buffer of tokenization between the actual piece images and the input to the transformer in our case. Yet, it achieves state-of-the-art results over ImageNet 3x3, so passing vision transformer models and very strong baselines. In the examples, you can see a fully correct reconstruction and a partial reconstruction. On the more challenging JPLeg dataset, on the 3x3 variant, we are second best, followed by a strong baseline. And on the 5x5, quite large puzzles, we are state-of-the-art in quite a big margin. And try to use them. but we found their representations are not well structured, in the sense that each token is really dependent on its position within the sequence and its neighbors. So we conducted this experiment where we encoded an image, switched some of the tokens. What we expected to receive is some kind of the right shuffled image, but instead we got deteriorated and global changes in the represented image. So this is what mainly drives the drop in performance when using deep image tokenizers. The second ablation was done on the seek-to-seek model. As I said, this is quite our framework is agnostic to the specific implementation of the seek-to-seek model. We did find out that attention-based models perform better by a margin, and that the length of the context is crucial for handling large puzzles. So to summarize, what we were trying to do was to challenge the current paradigms that this computer vision task, jigsaw puzzle reconstruction, must be based on visual features. We created this blind language model solver, outperformed many strong vision-based baselines, and created some kind of a bridge between the two disciplines. So I want to thank you. You are invited to go to the lab website or contact me regarding questions or suggestions for collaboration. So thank you very much.
Thanks. Questions?
My primary, okay, the question was why this handicap method works so well. My primary suspect is that we used a compact representation, which is really relevant to the problem. So we use only the tokens on the border of the pieces. The whole
information to infer the sequence to sequence, and if the patches are way too large, they're too unique, and again, you suffer. Have you ablated the size of the patch and figured out how it works?
Yes, we have, and in the paper we discussed that. Actually, there is a sweet spot and kind of a trade-off between the size of the patch and the reconstruction accuracy. Around using t equals 4, we get, on our test case, maximum accuracy.
Okay, let's thank the speaker again.
Thank you.
Okay, the next talk is from Rachman University, a talk about mockup anywhere. The talk will be given by Ofir Abramovich.
Hello, everyone. Good afternoon. So as Shai said, today I'm going to present to you our recent work. This is a joint collaboration with University of Cyprus, Andreas Aristudo, together with my Ariel Shamir and my supervisor from Reichman University. The name of the work is Mockup Anywhere Towards Pairwise Distance Motion Capture in the Wild and for the Wild. So motion capture, let's do a quick recap for those of you who are not familiar with the term. So what is it? Motion capture is actually the process of recording the movement of objects or people. As you can see there in the video. How is it done? There are actually three main approaches and technologies to apply motion capture. The first one is the optical base. As you can see there, a simulation of a studio surrounded by infrared cameras,
and it is known to have high precision for locating 3D positions in space. The second one, also very popular in the field, is IMU-based, inertial-based actually, or IMU, which measures rotation, acceleration, and angular velocity to approximate local behavior of joints. And the last one, which is less relevant for our talk, is the visual-based that takes as input the video. It's usually a neural network driven and applies the projection from 2D to 3D to recover the motion. Who uses motion capture? First, the industries, the film and gaming industries, for bringing characters to life in films and in video games. The second very popular field is the sports science for analyzing biomechanics for athlete performance, and for medicine for the analysis of movements of patients and for physical therapy. So these approaches have some limitations in them. Each of them has its pros and cons, and I'll focus on the cons for this presentation. And let's start with the optical-based. The optical-based has three major limitations. The first one is that it's super expensive. The more accurate, the more cameras we need for our studio, the more space, the larger the studio we need, and it's very not affordable for anyone. It can reach thousands of dollars. The second limitation is the constrained environment. Because it's in a studio and surrounded by cameras, then they bound an area that the character cannot go away. If he crossed the border of this restricted area, then there will be no motion captured. And the last one is the extensive configuration. Before starting a new session, one needs to apply calibration of all the cameras, ensure they are up to millimeter correct to produce the high precision that this system offers. And the IMU-based, even though it's more affordable than the optical-based and more portable, it's still less accurate. And the second limitation is that it's not stable, which means that when starting a new session and capturing motion, then every once in a while the character needs to be recalibrated again. And it's time consuming and pretty annoying, I can say. I tried it. And for the last limitation, which is pretty major, is the cumulative global drift. Since the IMUs are approximation-based and they approximate the pose from inertial measurements, they are not aware of the global position of the character. And therefore, it's very hard to approximate the location, and the error is cumulative. So as time goes, this error might be large and end up to a few meters away from the actual position. So considering all these limitations, there is a lot to be done. So moving to the related works, I'll be focused on this line of work, which is called Sparse Inertial Mockup. This line of work utilizes a small number of sensors. This is why it's called sparse, aiming to approximate the whole skeleton body. So different works have proposed to train different neural networks, add physical constraints and simulation and with varying architecture, but all of these still remain limited as they all use IMUs, and therefore they suffer from the limitation I presented in the previous slide. We want to tackle it in a different way, in a novel perspective. So before we dive into our proposed approach, I want to introduce you the ultra-wideband technology. This technology is a wireless radio system that uses short, high-frequency pulses for achieving precise real-time tracking. For example, the AirTags that most of you or some of you have, they use ultra-wideband. Car reverse sensors also use this type of technology, and this technology keeps evolving because it's very practical and useful. So consider a set of ultra-wideband sensors. It can be seen as an encapsulated, independent, decentralized network
that communicate with each other and produce us, at a given timestamp, a pairwise distance matrix. Well, for a set of size 6, the matrix will be 6 by 6. We propose a methodology, following to that, we propose a methodology that uses this kind of set by placing it on the body, and therefore define a new way for a 3D pose, simply a pairwise distance matrix. And so utilizing this technology allows us to perform motion capture in uncontrolled environment everywhere, and the coolest, to perform it not being restricted on human. So the key challenge for this work, well, using this technology is very challenging because the hardware has some embedded noise in it. And, sorry, just a second. Okay, so the key challenge for this work is that ultra-wideband suffers from errors, from noise. Sorry. Sorry. Legal. Sorry about it. So let's continue. So considering the key challenge for this technology is that ultra-wideband actually is based on a radio signals and often suffers from some error. Okay, so this error actually, I mean by the manufacturer, it's recommended to use for at least 5 meters, which is much larger than parts and distances among the parts of the body. So just for analysis, we take a sensors, put it on top of it, an optical-based system, and then compare the noise. You can see from the right that the smooth transition, implies for smooth and nice motion, as opposed to the sensor that we use, that much more jittery and represent a noisy motion. And we want to tackle it. So therefore, we introduced the wild poser model, or WIP for short. So this is a decoder-only transformer that leverages gated cross-attention for the interaction with past motions to produce the next one, given the corrupted measurement. So to make it all play together, we carefully define specific loss function that aligns with motion priors to help wild poser to reconstruct the natural motion. We apply losses to supervise the motion precision, the skeletal consistency, the auxiliary alignment, and for regularization for orientation and balance. So let's talk about some results. When no noise applied, it can be seen from your left that wild poser achieves smooth and precise motion reconstructions. This comparison actually assures that the potential under the lab environment, comparing to previous method. You can also see that the trajectory of the motion here is really similar to the green one. We are the blue. Okay, and as known, when shifting to the real world, things get a little bit more complicated and the general error increases. However, comparing to prior works, we show that we still perform better. You can see me there trying to box and my reconstructed motion using our method. And you can see from the graph below, we are the green line. And we actually show here that we eliminate the cumulative global drift which prior approaches suffer from. And not only in the wild, we also apply motion capture for the wild. In these experiments, we try to use our method on some animals. Don't worry, it's harmless. And we place our sensors on a donkey and a camel, and we actually managed to reconstruct their motion. We did it using some training augmentations and some tricks, but we managed to achieve a decent motion. And to best of our knowledge, we're the first to do it. So, to summarize, our contributions are, we propose a new methodology for mocap, utilizing the ultra-wideband technology. We dramatically reduce the barriers for in-the-wild motion capture. We propose a robust shape-invariant model for distance-based reconstruction, and hopefully encourage others to explore the field and continue this work and improve it even better. Thank you very much.
Thank you. We have time for a quick question. So, how many trackers are you currently using?
So we use the sparse setting, which is 6, okay, following other works. And when capturing animals, we had to use, actually we use the same number, but placing them differently. For example, the camel has a really long neck, so we place one there. And it doesn't have hands, so we place it on all the legs. So it was challenging for trying non-human beings.
How did you get the ground truth for the camel and the
We
animal?
didn't. It's just for qualitative results. We did not have nothing to compare to, but this was a kind of proof of concept that we had to try.
Okay, thank you very much.
Thank you.
And the next talk comes from Machon Vulcani and Haifa University. Talk will be given by Ron Bitton, and it's about animals as well. Sheep biometric identification based on multiple body parts.
Just a moment. Okay. So hello everyone. Good afternoon. My name is Ron Bitton. I'm a master's student from University of Haifa. Also, I'm a PLF lab member from Vulcani Institute. My supervisors are Professor Ilan Shimshoni and Professor Ilana Lachmi. And my thesis is about sheep biometric identification used multiple body parts. Modern agriculture uses new technologies to improve farm management, reducing costs, and optimizing workflows. A key part of this process is the ability to monitor and identify individual animal automatically. Today, RFID is widely used for automated animal identification. It allows individual tracking, but depends on physical tags and limited range, which can be challenging in real environments. Previous studies explored individual identification based on the computer vision and deep learning techniques. Three main directions that we can find in the literature are AirTag text recognition, face recognition, and individual cattle identification using multiple body parts. Our hypotheses are that sheep can be identified not by their face feature, also by their back and leg features. And when we combine multiple sources together, that improve the identification accuracy and consistency. Our approach is to combine together computer vision and deep learning for tasks like object detection, feature extraction, and classification. Our experimental unit is one drinking visit that are multi-frames, and after we get one decision, who is it in this specific visit? And our aim is to automated visit level ship identification under found tag without human involvement. The experimental setup consisted the following component: a water truth enabling natural ship visits, a PLF monitoring unit that developed at Volcani Institute for drinking and body weight data collected, an NVIDIA Jetson O-ring on the site for data collection and initial processing that after completed at the lab, and then Intel Wilson's RGBD camera that positioned primarily to get a body, different body angles, okay? These images show the system, how it's installed at the farm and operating during natural ship visits. Experiment details. The experiments were conducted at Ivr Farm, Azaria, Israel, 10 days in May 2024, from 6 a.m. to 7 p.m. A total of 287 visits collected of 85 different ship. Visits were detected using depth change within a region of interest with RFID used only for the ground truth labeling that we get from the unit that we showed before. Methods for body part, object detection YOLO V8 for detect the different body parts. Feature extraction, we use ResNet 18, ResNet 50, and clip. And for classification, we used MLP classifier to predicting the identity. For AirTag, we used object detection, again, YOLO V8 for detect the AirTag. And for the text recognition, we use a GLASS algorithm that developed at Amazon team. These frames illustrate the sequence of a single visit. At different moments, different body parts are visible and detecting by the system. All these detections are later used together for the individual identification process, which I will describe next. In the first stage, YOLO V8 detected body parts and hair tag, and the resulting bounding boxes were used for feature extraction and text tag recognition. There are some examples of annotated frames. Next, visual embedding were conducted using ResNet and clip, both commonly used for individual animal identification. And the best performing model was selected for several experiments. In the next stage, each body part was classified independently using a dedicated MLP classifier. Per frame probabilities were averaged together across all the visit, obtain one probability vector for the visit. This slide illustrates the aggregation from frame level to visit level probability vector. For the tag recognition, detected text strings were matched against a bank of true known tags. Text similarity was computed using Levenstein distance. And scores were aggregated across all the visits. These scores were then normalized to get a visit level tag probabilities, like we have exactly in the previous stage of the body part. Finally, prediction from the face, the back, the leg, and the tag weighted by their accuracy.
and fused to obtain the final visit level identification. It's important to note that 2 additional fusion strategies were evaluated for the final classification decision. A grid search was applied using different weight ranges for the individual sources, and ensemble model combining all the sources together also tested. But all the fusion strategies yielded a similar performance. So because of that, we choose the proportional weight for this simplicity. When designing the train test split, we encountered 2 main challenges. The first one is uneven number of visits per ship. And the second is since our unit of evaluation is a visit, we want that every visit had to be included in the evaluation process. Because of that, we have an iterative split strategy that we included only ship with at least V visits or more to ensure sufficient training data. In each iteration, V visits for any ship random selected. V-1 were used for training and 1 for test. The process was repeated until all the visits that we have in the data set are evaluated at least once. And if there are some repeated predictions, we averaged it. We have 4 main experiments: embedding model comparison, body part and tag combination, varying population size and varying training data set, fixed population size and varying data set, training data. EXP1 and EXP2 were designed to isolate the effect of population size and training data volume. Results. Table 1, embedding model comparison. ResNet 15 achieved a best performance across all the evaluation metrics. A slight good performance from the other. Because of that, ResNet 50 was chosen for subsequent experiments. This table summarizes visit level identification performance for different body parts, combination, and tag. Few key results. Using the back alone achieved the same accuracy and using the face alone. Tag-based identification showed lower accuracy but high precision. I mentioned that the camera placed in angle that got a good pictures of the body parts but not focused on the air tag. So because of that, we got a low accuracy but high precision, so it's reliable, more reliable when it's detected. Combining face and back together or face, back, leg together get a better accuracy than the single sources for 80% of accuracy. And when we add a tag to this, we get 85%. Here we compare the 2 settings that I mentioned before. Key results, face and back remained stable across both experiments, while leg alone consistently shows lower accuracy. When face and back combination consistently achieved high accuracy across experiments, while adding the leg provided only marginal and inconsistent changes. At higher visit threshold, face and back achieved 91% of accuracy, with a small addition of gain when adding the tag, the front tag. Peak accuracy, 93% when we combine face, back, and front tag, and 91% when we combine face and back. The 2 experimental settings produced comparable result, indicating that performance was more sensitive to training data per individual than population size. Limitation, single overhead camera,
with no side or rare views, uneven number of visits per ship. Identification was performed offline, not online, and reliance or RGBD and not RGB only. So because of that, there are future work, multi-view camera setup, longer data collection, a real-time system, and a transition to RGB only. Conclusion, an automated system for visit level identification was developed and validated on farm condition. Our two hypotheses are approved, that we can identification of non-facial body regions, and when we combine together a few sources, it will make the accuracy better. And body part features enable the accurate and non-invasive ship identification when sufficient training data are available. Thank you for PLF member, EveryFarm for data collection, European project Smart and Tech Care. For additional details, we are here. Thank you so much.
Thank you. Questions? In the meantime, the next speaker can come and set up. I do have one question. So the farmer can identify all the different sheep just by looking at their faces?
The farmer that we are being there with EveryFarm, yes, he can do, but not only by the face. For example, by their color of their back or their leg, something like that. This is really interesting. But there is some sheep that if you look only on their face, for example, they are very same face, so you cannot recognize. But if you look in other source, then you can recognize.
But then you might detect them or recognize them using gait as well. So motion might also be a cue, not just static parts.
Yes, but motion, yes, it's a nice idea for future.
Okay, let's thank the speaker again.
Thank you.
Next talk is going to be about hierarchy-aided deep segmentation, work by Noy Shargal and Micha Lindenbaum, and Noy will present.
Just a minute. Okay, so on this talk we are going to talk about hierarchy-aided for deep segmentation and silently object. Okay? Oh. Okay. So this talk we are going to talk about hierarchy-aided deep segmentation and silencing object detection models, how to use image hierarchy for deep segmentations. So hierarchy of segmentation is a classical tool for segmentation, which was before the deep learning era, was published and used by Malik and others. This tool basically was just abandoned in deep learning era, and in this work, we show how to use the hierarchy to improve deep models for SOD and class-agnostic foreground segmentation tasks. So I'm going to explain what is image hierarchy and how to represent it, how to fuse image hierarchy into deep models, and eventually we will conclude with evaluation on a moderate model attention unit. So first of all, let's explain what exactly the hierarchy is. So we split the image to small regions called superpixel. From these small regions, we build bottom-up a tree representing a hierarchy of an image. Every node in the tree that you can see here represents some region in the image. And those regions are grouped bottom-up by some dissimilarity matrix. So how exactly we do it? Oh, and I also want to say that if you understand how the hierarchy works, so the node, the main node, the root node of the tree is basically all the image. The superpixel leaves covers all the image. So in step one, we over-segment the image by generate superpixel. We used Slick, but you can use anything else. We also generate by edge detector, a head edge detector, a probability edge map, and we group superpixel by some similarity, which is defined by the probability edge map. So we specify this similarity between adjacent regions as the edge probability on the boundary between them. The bottom-up process, we merge adjacent regions starting from most similar region pairs. The hierarchy is represented using an ultra contour map. To use the hierarchy as an input to deep network models, we need to represent the hierarchy. We represent the hierarchy using a single channel UCM image. For every merging event between two regions, we add contour between the regions to the map, color it with dissimilarity of the two regions, meaning bright contours for strong dissimilarity and darker contours for weaker dissimilarity. It can be proved that the resulting map fully represents the hierarchy. So to summarize the generation of the ultra-metric contour map, the image is fed into two algorithms. One is Slick to generate the over-segmentation using, to generate superpixel, which covers the whole image. And with the head edge detector, we generate the edge probability map. As we explained in the previous slide, the hierarchy is generated to a tree, and the tree is converted to the hierarchy edge map called the UCM. The hierarchy fusion, in here, firstly, now that we understood what hierarchy is, I'm going to talk to the main part of this talk is how we benefit with the hierarchy in the model. So basically, in the light blue top region here, you can see typical segmentation model, which is fed by an image. And the output is basically a segmentation. It could be also silencing map, doesn't matter so much. And in the bottom yellow region is our proposed input and encoder. We feed as an input the UCM image, encode it with several scales, and each scale is fused into encoder and corresponding decoder stages. I also want to remind here that the UCM features, it's not new, it's in the image. So we just derived it solely from the image, not something else. We reduce resolution and increase channel dimension with the progression in the encoder of the UCM, and fuse it. The hierarchy cues are injected into both encoder and decoder pathways. Now I'll explain a little bit about the fusion mechanism. The encoder uses edge-guided attention, which is, it learns coefficient on the spatial axis between the derived UCM features and the derived RGB features. For the decoder, we used some more expressive mechanism. We added the squeeze and excitation module to learn coefficients for the channel dimension also to be more expressive. The lightweight mechanisms enable the UCM features to selectively adjust RGB features The generated fused features represent both semantic information from the RGB image and structural cues from the UCM. Advantages in implementation and training. The proposed method does not require many parameters. We use just 1.5 million parameters. It might be depend on the model that you enhance, but just the number of its encoder stages, it doesn't depend on the models and the enhanced model parameters. The training is standard. The UCM features serve as an internal structure guide with no need for extra prediction heads, ground truth, edge mask, or auxiliary loss functions. The design is also modular, and we can generalize it and use it in any encoder-decoder model with minimal changes to the architecture or the training pipelines, because we don't, I repeat it again, we don't use the derived UCM image in a loss function or something like that, or an auxiliary loss. We demonstrated the method on attention unit. As I said, in our module architecture just adds 1.5 million parameters. Attention unit, in this example with attention unit, includes 8.2 million parameters. And the experimental procedure is basically very standard for silency object detections task. We train on DATS-TR and MS-array 10K datasets, basically 20K images with some standard augmentation and standard loss function. The hierarchy does not influence the loss. Evaluation is performed on 6 standard datasets, which are well adapted in all SOD papers and benchmarks. And we evaluated the results with 4 standard performance metrics, MIOU for segmentation and other metrics for silency object detection task. In this table, we can see the quantitative comparison, baseline versus our method, the hierarchical deep segmentation, HDS. We can see here that we have the 6 data sets for evaluations, and our method improves model performance in large gaps in all metrics. From qualitative comparison, we will see that most corrections are around boundaries and on hard classification pixels. Also, if we look at a precision recall curve, we can see that our method improves the model on all data sets and all thresholds. I give you some qualitative comparison to see some examples. You can see that, let's take an example, the plane in the bottom picture, the bottom image. There are, in the tail of the plane, it's colored with some colors, so it's hard to classify it. And the vanilla attention unit model find it hard to classify it, but our model fixes it. You can see also the sailor here. Basically, everywhere it was hard for the vanilla model to perform well because some region was very similar to the background. Our model fixed it. Our conclusion is that the integrating explicit hierarchy as an auxiliary input significantly enhances moderate-sized deep models. It improves performance. We demonstrate it consistently on core segments metrics and also on boundary accuracy for class-agnostic foreground segmentation and silency tasks. The moderate models are used for edge devices. For large models and transformers, we still need to see if using the explicit hierarchy is effective. Thank you for your time. It was very nice to talk here.
Thank you. Questions?
Sorry? For? You mean like segmenting small objects?
Small details. Or
Yes.
let's say the small details even of larger objects.
I can show you as I showed in the images here. You can see here like okay. What do you call small? Like these data sets have basically big objects on a background. There are some data sets for semantic segmentation with special for small objects. We didn't test it on these data sets yet, but I guess we will in the near future.
Okay. Any other questions? So let's thank the speaker again. And the next talk from Bar-Ilan University on modular OCR using web scraping data. Talk will be given by Guy Gisman.
Okay, hello everyone, and thank you for being here. My name is Guy Gisman from Bar-Ilan University. This is a joint work with Dr. Eli David-Omid and Professor Natan Netanyahu. And in this presentation, I will show you how web-based data can make modular traditional OCR surprisingly good. So let's begin with the challenge. OCR system needs massive amounts of training data. And when I'm talking about training data, I mean for both detection data and recognition data. So several solutions have been proposed in the literature. One very common solution is to use PDF pages. But PDF pages tends to be very clean structure with mostly predictable layout and mostly contain formal language. Other solutions for OCR are painfully manually labeled dataset or fully synthetic images. Both solutions are very hard things to do in order to get large, diverse, or realistic dataset. So what if we use the web itself? So websites come in every imaginable fonts, linguistic styles, layout, and designs. So, for example, websites can contain sidebar menus, pop-ups, and paragraphs can appear in a very diverse layout. So in this example, we can see a screenshot, and on the right, we can see word polygons in blue and image polygons in red. And one important thing to notice here is the logo on the top left corner. This logo is actually an image that contains text that we cannot parse, unless, of course, using an existing OCR engine, but we don't want to assume that we have an access to one in this work. One more thing is to notice here is all of the text instances that are floating on top of images or other objects. So as long as the text instances are visible to the user, we extract them. So actually, web-based data already proposed for LVLM-based methods, but we are the first to use it for the modular traditional approach, which tackle some new technical challenges which I will explain soon. So our main contributions are as follows. As I said, we are the first modular approach that used web-based data for generating and for training an entire OCR pipeline. The second one is online augmentation. So we don't just capture website screenshots. We can actually edit the websites on the fly before taking the screenshots. So if, for example, we want an handwritten OCR dataset, we can just swap the fonts of the website to be handwritten fonts. The third thing is the loss masking technique. So this is a way to handle images or logos that contain text that we cannot parse automatically. So instead of poisoning the training with false negatives, we ignore those regions during training. And of course, performance-wise, we achieve competitive or superior results, especially in noisy environments. So let's compare our approach to an existing LVLM-based OCR method that used web-based data. So as I said before, training modular OCR based on web screenshots tackle new technical challenges. So for example, LVLMs don't necessarily need text localization labels because they can be just trained in an end-to-end manner. Other LVLMs that use text localization labels can settle for coarse text localization labels, such as paragraph bounding boxes, or coarse word bounding boxes, such as bounding boxes with paddings. However, in the modular approach, when training a word segmentation model, we cannot settle for coarse bounding boxes because in a case of dense text, overlapping bounding boxes with margin or paddings can overlap, so all ends up in the same connected component, which is very problematic in our case. One last thing to notice here is that handling embedded images in web pages is not so trivial, and some LVLMs were trained on reconstructing the HTML tree instead of predicting the entire text, which are kind of different tasks, right? Because imagine training a model to predict an image HTML tag instead of predicting the actual text inside of that image. So this is a high level of our data generation process. We have 4 main categories of steps. So the first step is to extract word bounding boxes. And we are doing so by making each word as a separate DOM element in the DOM tree, so we can extract a coarse bounding box of it using JavaScript. The second one is to extract image locations, so we can mask them out later during training. The third one is handle a lot of special cases. Believe me, websites are not so trivial today. It's very challenging. So things like word breaks, pop-ups, animations, shadow root elements, input place orders, and so on. And lastly, we make a refinement. So in order to get precise word level annotations, we make a post-process, a refinement to remove word paddings and maybe to merge adjacent bounding boxes when necessary. So this is an example of an output of our data generation process. So again, you can see word polygons in blue with their extracted text on top of them and image polygons in red. And this is a simple example of a refinement, a post-process that we do in order to get much more tight bounding boxes. So we have a crop of a website here, and let's say we want to extract the bounding box of the word milestones. So we can see that JavaScript return the word with a padding, in this case top paddings and bottom paddings. And again, in the case of dense text, all the words might handle in the same connected components if we allow these paddings. So we want to somehow remove that padding. So what we do is to make this word transparent, and then we compare the two sub-images, pixel by pixels, And then the difference between them can be wrapped by the true bounding box. And this is another example of a refinement that we do. So sometimes web developers decide to use more than just one HTML element in order to describe a single word. So we need to make a post-processor refinement that merge subwords into one single word. In this example, the word here is a separate subword since the word here is actually linked, so it's described in a separate DOM element. So we decided to classify our data augmentation techniques into two types. The first type is offline augmentation, which is the image level transformations that we are all familiar with. Things like convolutional filters, noise addition, color transformation, compression, perspective transformation, and even blending with background image. And the second type is unique to our approach. It's what we call online augmentation, which again allows us to maybe swap fonts in website before capturing the screenshot, or even change the text content in order to minimize maybe a domain gap to a target distribution and still enjoy the diversity that the web contains. So this is an example of online augmentation. So we can see an original website on the left, and the same website after changing its font to be a read and written font. And this is an example of combining both online and offline augmentation. So in this example, we started with a Wikipedia page. Then we apply an online augmentation. We swap its font to be a handwritten font. Then we capture a screenshot, and then we apply several offline augmentation techniques. So our model architecture is intentionally straightforward in order to emphasize our data generation process, the innovation of our data generation process. So for the word detection module, we actually use a word segmentation model together followed up by a connected component analysis in order to transform the predicted mask into predicted bounding boxes. So the loss function of our vanilla unit is described below. So we use a class balance cross entropy with two coefficients, W background and W text. And those coefficients are the inverted frequencies of background and text pixels, so the model doesn't get biased by the overwhelming majority of background pixels, all multiplied by a binary mask, I mask, which exclude uncertain regions like images from backpropagating noise during training. And then we have a word recognition model, which is a ResNet with a transformer encoder on top of it. And then we have heuristic-based layout analysis tool that give us the correct reading order. So actually, instead of training on the real websites, we decided to use open source web templates that developers freely share. And thanks to our online augmentation techniques, we transformed those templates into rich and diverse web datasets. And this choice had two big advantages. The first one is that we decided to not deal with any copyright issues of crawling real websites. And the second one is to avoid the cybersecurity risks of crawling real live websites automatically. So to evaluations, so we evaluated our model against several state-of-the-art LVLMs as well as two commonly used modular OCR approaches, Tesseract and Easy OCR. And we evaluated on two data sets, very different data sets. The first one is the Fox data set, which consists of PDF pages. And in this data set, we achieve a very competitive, almost as the best LVLMs that saw PDF pages during their training, and with much fewer parameters. And the second data set is the Silatus data set, which consists of real website screenshots. This data set is much harder in terms of layouts, fonts, and linguistic styles. And in this data set, we achieve the best results. And also, when averaging both data sets together, we also achieve the best recall and F1 score. Lastly, we define two a group of real-world noises. The first one is geometric noises, and the second one is additive or filter-based noises. So we can see here an example of clean sample on the left and a noisy version of it on the right, mimicking some real-world scenarios like motion blur. So under geometric distortions, while LVLM lost between 25 to 28 percentage points of F1 score, our model lost by less than 11. And under additive or filter-based noises, while LVLM lost between 20 to 30 percentage points in F1 score, our model fell by less than 16. So this demonstrates much more resilient to real-world scenarios. And to conclude, we show that modular OCR system when trained on diverse web-scraped and augmented data can match or even surpass state-of-the-art LVLMs and widely commonly used modular approaches, particularly in real-world noisy condition scenarios. So modular OCR is not dead yet, and I personally think that it also deserves the innovations of data generation techniques that mostly LVLMs enjoy these days. And looking ahead, our next step is to extend this approach to other document analysis tasks, such as table extraction and form understanding. And my vision is to build an efficient and modular document analysis system that is made up of multiple lightweight task-specific models that can be activated depending on the input task, all trained on the same web we all browse every day. And thank you very much.
Questions? So
is the edit distance inside those words? Yes, word levels.
okay, thank you. Let's thank the speaker again. And the last talk of the day by Avi Pelt on phase spoofing or anti-spoofing? Both. Okay.
Okay. Hello, everybody. My name is Avi Pels, and today we'll talk about computer vision beyond RGB, using a sparse polarization biometric as a case study. This talk draws primarily from our paper on the effectiveness of sparse linear polarization pixel for face anti-spoofing, a joint work of Tel Aviv University and Cophotonic, a Samsung company, led by my former colleague Jay and supervised by Dr. Schrer and Professor Mendelovich. Let's first talk about image sensor design. Classic image sensor design rely on free RGB channels, while modern sensor design sparsely incorporate spatial pixels. This low-resolution data is significantly more informative for some computer vision tasks than the high-resolution RGB data. Otherwise, no one will use them. In this case study, we evaluate the effectiveness of sparse linear polarization pixels for biometrics. But what is polarization? Light is characterized by frequency, e.g. color, amplitude, brightness, and polarization. The latter describe the geometric orientation of oscillations. Let's look at a classic example of a light wave. The angle of linear polarization is the direction in which the electric field oscillates. In this example, the light is purely linearly polarized. Of course, not most light waves are not purely polarized, as can be seen here. The share of intensity that can be explained using a single angle of linear polarization is the degree of linear polarization, here 100%. Most important for us as computer vision practitioners is that the angle and degree of linear polarization from a surface provide Q but is characteristic, exactly like color. But how do we measure polarization? It is possible to split light into 4 polarization states or angles. The same way it's possible to split it into 3 RGB colors. However, when both pixels are used together, as done in some commercial sensor, it results in 50% drop in both the RGB both resolution and sensitivities. An alternative was recently suggested. Using a sparse polarization sensor, where most of the pixels are RGB, and only a minority are polarization pixels. Visualized here are 6% polarization pixel. By demosaicing the RGB pixels, we get an high resolution and sensitivity RGB image. Meanwhile, we can use the polarization pixel to get low resolution polarization data, and with some processing, we get the angle and degree of linear polarization. But why do we want to measure polarization? Let's look on a human face with 4 polarization angles. Due to its 3D surface, each polarization angle has a different intensity, as we can see here in the cheek area. However, if somebody tries to spoof a face by printing it, all the polarization, if they will get a 2D surface, and all the polarization will look the same. If we try to replay the same photo on a Stardust display, the difference between the polarization will be much larger, because light emitted from such display is highly polarized. In conclusion, we can detect face spoofing attempt using this data pretty easily. Let's look on the data itself. Genuine face have a high contrast signal that can be seen here, while the printed spoof is flat, is noisy and flat. The replay spoof is also flat, but it also has a high degree of polarization visualized here with the blue channel. Our case study is ultra-sparse polarization for face anti-spoofing. In other words, we suggest a sensor with ultra-sparse polarization pixels, where most of the pixels are RGB and can be used normally for photographic or face recognition, while tiny minority of the pixels are polarization pixels, which are used for face anti-spoofing. This patent-pending technology is an alternative to existing solutions that require additional sensors, like depth sensor, with higher cost, weight, and power consumption. We can simulate sparsity by sampling the dense polarization data. Here, we visualize the sampling dense polarization data down to 0.25% polarization pixel density. In other words, 1 out of 400 pixels. And we can see that the spoof still stand out, even in this low density polarization. This means we can safely dedicate 99.75% of the pixel for photography, while having a reliable face anti-spoofing system with no additional sensor. In principle, polarization highly discriminated nature enable a simple feature-based anti-spoofing method. But we train on network to enable a comparison with RGB. Our methodology is pretty simple and straightforward. We repeat 100 training sessions for each input data, and for each session, we randomly sample train validation speed. Then fine-tune a pre-trained backbone with binary classification layer, e.g. genuine versus spoof.
Finally, we average the validation result across all training sessions. The result we get using the average classification error rate metric is 4% error for the RGB-based neural network and 0.3% error for the dense polarization-based neural network. A tenfold reduction in error. This means that polarization is highly effective for this task. The second takeaway is that neural network trained based on ultra-sparse polarization data, again, 1 out of 400 pixels, reach almost the same error as the one based on dense polarization. This means that ultra-sparse polarization is enough for this task, and we can safely use the rest of the pixels for polarization, for photography. This proved our claim. But let's look on more details. Let's talk about how to represent polarization. The first question we ask is, do both the angle and degree of linear polarization support phase anti-spoofing? The answer is yes, but the angle is more discriminative due to its stronger correlation to phases 3D structure, and we'll show this empirically in the next slide. The next question we ask is one channel enough to represent the angle of linear polarization? The answer is no. Single channel representation causes discontinuity to orientation cyclic nature. This means that 0 degree orientation and 180 degree orientation are exactly the same, and it's impossible to represent this kind of behavior continuously using a single channel. The solution is pretty known for this kind of cases. We use 2-channel Cartesian representation, as was previously done for rotation. And this solution, of course, also improved the result significantly. We verified our answer using the following tabulation. We train model with different representations with varying training set size and plot the results in log-log scale. Our finding is that our representation achieve the lowest error for any train set size. Using the angle of linear polarization alone, i.e. without the degree of linear polarization, double the error. And using the same angle, but represented it with a single channel representation, double the error again. Finally, using the degree of linear polarization only instead of its angle increases the error more. So both questions from the previous slides were answered empirically here. In the paper, you can also see the physics reasoning behind this. For conclusion, the key takeaway are, we first showed that ultra-sparse linear polarization, 1 out of 400 pixels, is more discriminative for phase anti-spoofing than the full RGB data. This will enable cheap and reliable phase biometric on low-cost single-sensor devices. The second takeaway is that small data ablation can evaluate data effectiveness without full training. This is based on the underlying assumption that less informative modality or representation require exponentially more data for the same accuracy. This is critical for real system development, of course. If you like to read the full paper, you can scan the QR code here. Thank you for listening in this late hour. I'm now happy to take any question.
Thank you. Questions?
I think I'm missing something, but as I understand, like the idea of spoofing a face is some sort of image generation. But then if you generate a ready image, then you're bypassing the acquisition.
Yes, but in real life, you try to look, let me go to the beginning, sorry. You're trying to enter a system like a phone. Phone is a simple and the most common example.
And instead of showing your own face, you're showing a picture of a face. So a picture of a face is naturally 2D and not 3D. So the polarization adds more information, mainly 3D information. It's a bit more complicated so you cannot generate it in, you need to print a 3D face, and also, I think polarization will find this also but it's a bit more complicated.
Any other questions? Okay, this concludes our session and the entire Vision Day. Thanking all for sticking so long, and have a great evening. We're done.